Good morning, ladies and gentlemen. Very warm welcome from me. My name is Rob Stevens. I'm your host. I'm one of the founders and directors of Interconnect. I understood that there are not only 60, 70 people here in the room, there are also from abroad, from home, a lot of people, even as far as South America, I just understood. So also for a very warm welcome or night, perhaps.
Rob, maybe you need to use the microphone for the people online.
Okay, I'll switch to the microphone. Very warm welcome again, also for the people at home watching this show. It's my pleasure to be the host today. I'll be introducing your chair in a minute. First of all, I would like to give you two house-holding notes. Maybe not necessary right now, but if you need a toilet break, they are at the rears of this room. You go upstairs and then there's a stair going down to the bathroom. And the second note from me is that the bottles of water that are here in the room should stay in this room. So if you would like to drink, do that here. Don't let the water get out. Thank you very much again for being here. Your chair of the day is Peter Salemink, to my left here. Peter, I hand over this to you. It's a pleasure again to be hosting you and your colleagues. I wish you a very nice and informing day. Thank you very much.
Yes, thank you, Rob. Thanks for having us here. Well, I think it's fair to say that this is a really nice location for our meetup. So really happy that we could do it here. Welcome all at the 7th Power Grid Model Meetup. To those in the room, but also the people watching online. There are quite some people that subscribed online as well. Reflecting on how we started 5 years ago in a small meeting room at Alliander with our first meetup, I think it's amazing to see so many different companies both attending physically as well as online. So really happy to have all of you on board, and I think we have a really interesting program today. So before we start, I would like to thank both Interconnect and Brightcubes in helping to organize this event with us. And I think we can start. But before we start, safety first. There's some things that I have to say. So in case of an emergency, please follow the signs of the emergency exits above the doors and listen to the instructions from Interconnect personnel. Also for the people online, don't drive and call. Also not hands-free. Just a note to everyone, the session will be recorded and photographed as well. And if you're attending online, you can post your questions in the chat. There are moderators here sitting with a laptop. So your questions will come through. So let me introduce myself. I'm the chair of the session today. My name is Peter Salemink. I'm also the chair of the Power Grid Model project at LF Energy. I'm working at Alliander as a product owner and scientific software engineer. And I'm also a guest lecturer at the Eindhoven University of Technology, where I try to bridge the gap between what academia teaches and what we as a DSO need. And of course, our students also use Power Grid Model. So we have a really interesting agenda for you today. There are many speakers, many different companies. So we're almost done with the introduction. After that, we'll start with the maintainer presentations, including the highlights and roadmap for both Power Grid Model as well as Power Grid Model DS. And then at the end, a short explanation of how to contribute to any of the projects. After that, we'll have our first use case presentation from Ankur Arohi. And then afterwards, we'll go to the Skybar for lunch. So if we get back after lunch, we'll start with a keynote from Martijn. He's doing the keynote on behalf of Bright Cubes, but he's also one of the maintainers of the Power Grid Model project. Then we go to the second use case presentation by Francisca Mestre. Then we have a short break. Then we stay here in the auditorium. We have our third use case presentation by Udo Schmitz and Eduard from SOPTIM. And then we have 4 lightning talks. So those will be really short, but really interesting. I saw the slides already. By Willemijn Brus, Leo van Schooten, Cyril, Cecchinel, and Wadman. And we end with a tour through the data center. The curtains are still closed, but the server rooms are behind. So we'll go on a nice tour that will lead us to the drinks at the end of the day. So I'm really looking forward to this program. I think it's the most presentations we had so far on a Power Grid Model meetup. I think also really interesting presentations aligned for us. So I will stop talking because there are a lot of people that have more interesting things to say than me. So we get to our first technical session, which is updates from the maintainers. And we'll start, so there will be highlights of the last year, the roadmap, and a short explanation on how to contribute. And the first maintainer I would like to call forward is Santiago Figueroa Marique. He's one of the maintainers of the Power Grid Model project, and they'll walk you through the roadmap and the highlights of Power Grid Model. Let's give a warm welcome to Santiago.
Good morning, everyone, and thank you for being here. Before I start, well, my name is Santiago Figueroa, as you already heard, and I'm one of the core maintainers of the Power Grid Model. And before we get into the details with the highlights and the roadmap, just to get everyone in context, let's talk about the Power Grid Model ecosystem first. So, right. Okay, perfect. So, right in the middle, this is an AI-generated image, by the way. We have the Power Grid Model, which is a calculation core engine, and it's designed to do high-performance grid calculations. Then, over the left, we have a Power Grid Model I/O, which is the library to do the integrating, so basically data conversion from other libraries like Panda Power and Vision. And then on the right, we have Power Grid Model DS, which is like a Python wrapper built on top of a Power Grid Model. To extend these capabilities, it provides additional features like visualization tools, graph tools, etc., and it makes it easier for you to handle the Power Grid Model. Now, let's begin with the actual highlights. This is no spoiler list of the things I'm going to talk about. So first, a couple of milestones that we reached last year. Then some notable features. We can't cover them all, but some things that we thought were really nice to mention here. Some bug fixes and deprecations coming, and also a shout out to the community. Now, on the features, you'll see that here on the lower right area of the slides, there are the credits of who contributed to this, because not everything was done by us, but also some external contributors. So let's begin. This is the first milestone that I want to highlight, is that we have reached more than 10 million downloads. So this is great to hear. If you remember, maybe last year, if you were here, we announced that we had reached about 3 million downloads. That was including only PyPI. But now, if we consider PyPI and CondaForge, we have surpassed the 10 million downloads. That is, of course, including automated downloads, so CI and so on, which is actually a good thing, because that means we're being used in production. So this shows you how mature and how much we're growing as a community. Now, to celebrate this milestone, this is a little surprise. At the break of the 2:25 in the afternoon, we'll have some cake here in the auditorium, so save some space for that. Now, the other milestone that I want to highlight is that now we are in the LF Energy landscape. We have earned the early adoption status. So last year, we were in the incubation phase, and now we're in the early adoption. But what does this mean? Basically, in summary, well, first of all, you see us over here, along with the other projects that are also in the early adoption phase. And in very short, it means three things. First is that we got the OpenSSF best practices silver badge. That means that our security standards, documentation, coding practices, and we have a clear roadmap, so that is a very mature project. That's number one. And the other two things are, first, that we are mature and ready, so we're production and industry ready, and that our open source community is growing quite a bit. So then this is another way to show how mature and big the power grid model is getting. So let's celebrate for this as well together. And now let's get to the content. So the first feature that I want to highlight is current sensors. So this was released in version 1.12, and this was a contribution by the PGM team. Now, it is supported, of course, it's a sensor for any state estimation calculation, but let's see a bit how does it look like. So we have two types of current sensors, local angle current sensors and global angle current sensors. Let's begin with the first, with a little code snippet. If you want to add it, this works exactly the same as any other regular sensor. You can attach it to a branch, for instance. You can define what type of sensor do you want, and you have some measurements under sigmas that you define. Everything works exactly the same. Now, if you want to have a global angle current sensor, the only difference, or it has two differences. First is that you specify that is a global angle current sensor, but also, as the name indicates, you need to include a voltage sensor or a phase or voltage sensor in your grid, because you need a reference angle for this to work. Now, 1 year ago, this was an experimental feature, only partially supported. Now it's fully out, not longer experimental anymore. And maybe one last remark, mixing sensors or current sensors of different types, or mixing power sensors and current sensors on the same terminal is forbidden. Now, let's go to our next highlight, which is the meshed observability check. This was done in collaboration of the PGM team and Mark van Raalte. Basically, before we get into the details, what is an observable grid? So when you're trying to do state estimation calculations, right, you need to have enough independent sensors in order so we can determine the correct state of the grid. When you don't have enough of these sensors, then we call that your grid is not observable. Now, in this feature, what we did is that we extended this check so we can cover mesh grids. So how does it look like? Let's consider this quick example of a very simple grid. We have one source, 4 nodes, and then we have a little loop here with 4 lines. And we have some voltage sensors and power sensors. However, if you see here, we have 2 branches that are unmeasured. That means this grid is not observable. Today, with this new feature, what you will get is a not observable error instead of sparse matrix errors. That means that you get a clear error of what's going on instead of the cryptic sparse matrix error. However, there is a caveat. Basically, if you have voltage phasor sensors, then you still get sparse matrix error. That's something we're still working on. But if you don't include that component, then everything is working great. Let's go to the next one. Now we have the Cartesian product of batch datasets or the multi-dimensional batch calculation. This feature was released in version 1.13, and it was done by the PGM team. Now, so actually, let's go first with an example to explain it a little better. Let's imagine you have 2 completely different types of update datasets. One is time series, and the other one is n-1 mutation. So for instance, in the first one, let's imagine that you want to increase some of your loads across 5 different scenarios, and in the second one, you disconnect some of your lines across some other scenarios. Now, if you wanted to have the combination of all of them together, you would have to manually create the new update batch dataset yourself. However, if now with this new feature, you list both of these independent datasets as a list of the 2, then we do this for you. Basically, we do that combinatorial combination of them. But how does this look like? So let's get a nice example here. Let's say we do the first update. We have two scenarios, and we have two lines. We have one connected, one disconnected, and then we switch it around for the second. And we have a separate update in which we have one load that is smaller compared to the other, and then we switch it around for scenario 2. If you now use the Cartesian product of batch datasets, you will get this as a result, where you consider all the previous combinations. Now, there are a couple remarks that need to be considered. The first one is that since we do this internally, you save a lot of memory because you don't have to create the ginormous update dataset yourself. However, keep into account that the resulting dataset is going to be flat for one, but this can grow quite quickly. So just be aware, but it's a very nice feature. And one last remark is that the validation doesn't work directly on this Cartesian product of batch datasets because it's just a list. So if you want to validate this before you try it, you have to individually validate the batch datasets yourself. Now, let's go to this other feature, and this one was actually contributed by an external contributor, so thank you for this. So last meetup, we presented that we had introduced the component data types and dataset types in order to get rid of the string component types and dataset types. But this feature was sort of incomplete because we were still missing the attribute types. Well, with this contribution, we now have it complete. And the only thing you need to do is, well, import it. But how does it look like? So before this contribution, if you will define one component, for instance, a load, if you wanted to define all its attributes, you have to use strings. But now we have these nice attribute types here. And well, at first it doesn't look like much, but this enables several things. So first, code speaks by itself. Clearly, you now have type checkers enabled, you have auto-completion, and it's a lot easier to avoid making mistakes because of a typo. So yeah, this is another one. Let's go now to this one. I'm going to mention it very quickly because as you saw in the agenda, there is a big talk. So this is about PV nodes. So if you want to know all the details, don't miss at 14:40 the talk by SOPTIM, PV nodes in PGM power flow theory and scenario-based demonstrations. Of course, it was contributed by them. So please tune in. However, just for you to know, for now, it was released in version 1.13. It is supported for Newton-Raphson power flow, and Q limits are not completely handled yet. Maybe a little bit of context. What is a PV node in this sense? Basically, we have buses that now can have generators that are regulated with Q, or the reactive power. So we can control the voltage and the active power with the reactive power. Now, please tune in. Don't miss the talk later on. And thank you, SOPTIM, for this. This is one of the other features we're working on. And actually, this one is a work in progress. We call it merging links into nodes. And it's actually, as you can see, a very, very old issue. Before I get into the details, we can split this into parts because it's a bit complex. So first, the math workout, which is basically a fancy way and very neat way of doing a Penrose inverse, if anyone knows what that is. This has already been done and implemented, and the credits go to Mark van Raalte. And now the PGM integration and implementation is work in progress, and it's happening with us, the PGM team. But what does this mean? So let's consider a very brief example. Let's say we have this simple grid with a source, two nodes, a load, and then just a link. When we try to run any type of calculation in these links, because the way we model links, basically very small admittance, then this can very easily introduce numerical instabilities. Now, the idea, roughly, is that we want to merge this node, connecting this link with this node, into what we call a supernode. So now the grid would look like that. So when we do perform the actual calculations, we don't have such links. And of course, the supernode has some internal structure that we need to handle, but that's details. But what this will do is that it will get rid of all those sparse matrix errors that you can usually get because you have links present. So stay tuned for this one. Now, of course, due to time constraints, I cannot mention all of the contributions. And I also wanted to highlight some of the other interesting ones or ones that we consider big enough here. So a small shout out. So first of all, we have Python dep containers. That's done by Lorena. So if anyone wanted to contribute to the Power Grid model as a developer from the Python side, well, we have a container that sets everything up for you. You don't have to worry about that. We now support natively UV. That's done by the PGM team. So basically in our pipeline, everything is done by UV, making it faster, cleaner. You can track dependencies, etc. The short circuit source parameters now are updatable, so a little quality of life feature that's also done by PGM team. Now, another feature by an external, so thanks Clemens Corner for this, it's that we have introduced, or he introduced, some additional Python helper functions like deep copy and some additional bundles to make your life easier to work with the Power Grid model on the Python side. And now, finally, we've been doing a lot of refactoring, internal refactoring, just to keep the code maintainable, readable, and performant, which is one of the things that distinguishes us. Now, done with the features I wanted to highlight from the past year. I want to get into some bug fixes that, again, I consider interesting. The first one, thank you WinAPMant for helping us find it and solving it, is we had a bug in the YYN transformer modeling. Basically, so there is a new attribute that we had introduced because the magnetization current was not modeled correctly for 3-leg core type transformers. So a lot of details, but now that is correctly fixed. We had also a bug in the fast any tap strategy if you were using automatic tab regulators. If you had a very, very tiny event, so the behavior of this strategy was different to the rest. Now it's homogenized. And we also had a Python multi-threading corruption. That is completely fixed. And then actually these other two bug fixes were also found thanks to the help of WinAPMan, another external contributor, and are related to the API. So on the right, we have the owning dataset bug. Basically, we were creating some wrong buffers on the CPP API. That is fixed. And on the green, we had a bug in the Python API. So when we had components for a calculation that were irrelevant, let's say sensors for a power flow calculation, we were creating, again, buffers for the output, which is not necessary. But now this has all been fixed, so thank you for all the contributions from the team and, of course, the externals. Now, of course, we have a list of deprecations. So as you know, this is kind of a reminder. So we have a release strategy in which we support the latest 3 Python versions. So we support currently 3.12, 3.13, 3.14, but it is expected that we drop 3.12 in January 2027. So please keep this in mind. And then there is another thing that we want to highlight is that there is no clear timeline yet, but Apple will drop support for Intel-based Mac OS sometime soon. They said this when they release Mac OS 27, so it's very likely that we're going to drop support for Intel-based Mac OS as well. So be aware of this. Now, let's give some shout-outs and highlights to the community itself. So first, just a couple of pictures from us in different events we were fortunate to attend last year, including SIGRE in the North America, LF Energy Summit in Europe, North America, among others. So you see some of us there just taking PGM worldwide, if you will. So that's very nice. But also a shout out to the whole community. So we now have a lot of where that is positive, but I hope a lot of you are there, and if not, maybe next year. But this is all the people that have contributed to the whole PGM organization, including PGM-DS, PGM, but not only features, but also issues, comments. Again, non-exhaustive, but it's increasing quite a bit. So I want to give them all a shout out. Now, of course, I can miss it. A shout out to our community meeting. So we meet every 2 months, more or less. You can scan that QR code, go to the link, and then you will find you'll get an invitation. We do announcements, use cases, discuss examples, features, demos, but not only from us, but from the whole community themselves. So you're very welcome to join. Now, I'm done with the highlights for now, but I'm going to jump straight away to the roadmap. And let me talk about what we are doing right now. So we're working mainly on 2 things at the moment. Basically, we want to expose a logger from the core. That means you can do potentially benchmarking or expose internal math that you couldn't access before, or logging in general. So we're working very hard on that. And the other thing, which I mentioned already in the features, is we're working on the merging nodes connected by links, which is a very big feature, and that it's going to be very impactful. Now, because merging nodes connected by links requires us to remove the support for sensors or power sensors on nodes. This was announced previously and discussed in the bi-monthly meetup, and also via the LF Energy mailing list. We have to remove this. So this means deprecation. This means breaking change. So we're going to probably do a major version bump soon after we have finished that. And then this is for you to be aware. Power sensors and nodes no longer supported, and also some Python functions, old versions of serialization and deserializations that we had marked as deprecated will be removed. So please be aware. If you have concerns, if you need help to migrate, please don't hesitate to reach out to us. And now, the rest of the things that were going to happen next. So we're thinking about current magnitude measurements. So right now we have current sensors, but you need both the magnitude and the angle. So we want to provide a sensor only with a magnitude. That's what's probably going to happen next. We have some bugs in the short circuit calculations. Those need to be addressed. And by the way, if you're interested in looking at any of the details, in the previous slides, as long as in this one, I have a reference to the issue or pull request on GitHub, so you can get more details if you're interested. And of course, another shout out to SOPTIM. They're going to continue their work with PV nodes, Q limit handling. Now, what will potentially happen very, very later on, we're thinking about providing a Java interface for PGM, which I think is going to be really nice. We are thinking about providing a continuous tap changer. So right now it is discrete, and we are thinking about extending it. We are also thinking about continuing on the working on the LF Energy graduation phase and reviews. So actually, there's an interesting thing here. Another company, external, will do a security check for us, third party, so we can comply with that. So that's something good that's going to happen. We're thinking about completing the observability check. That means not only providing support for phasor voltage sensors, both in radial grids and mesh grids, but also perhaps providing information about unobservable islands. We'll see. That's on the horizon. And then lastly, the uncertainty margin for state estimation. Basically, we provide some errors or sigmas in the input for the sensors. What's the error in the end, more or less. Of course, this is not set in stone. This is going to change, maybe not with the input from the community. We are here to shape it together. That is why this is a QR code for the GitHub roadmap, where you can see all the details, links to the issues, to the pull requests, and everything like that. And please help us shape it together. Again, not set in stone. We're here to build it. And now, maybe one question that I have for everyone attending here. We have thought about this. So currently, we cannot terminate calculations, for instance, from a keyboard interrupt, Of course, this is only applicable for, let's say, local testing, not cloud environments or containers. Would you want to use this? Would this be of interest? We want to ask because it requires, it's a bit difficult to implement currently. So if you require it, please let us know and we can put some effort, but we just want to get your feedback. You can let us know later on, or if you want to say it now, well, you're welcome. But just also, if you have any feature requests, please, our issue board is always open, just right there, or just approach one of us. I think most of us have a PGM shirt. You can recognize it. So just reach out and we can discuss anything. And I believe that is it from me. So thank you very much. And I hope that gave you a good overview of what happened last year.
You have 6 minutes for questions, if there are any.
All right. Any questions or maybe any input on the question we made about keyboard interrupt? Would it be useful, maybe, or not? Yes, guys.
So yeah. So regarding your question for the keyboard interrupt, in my experience, but maybe you can clarify a bit. But in my experience, like it's always really fast. So I'm only interested in interrupting a process when it takes maybe like 10 seconds to do a power flow calculation, but normally it takes only like 1 second. So then for me, I don't really see how it would benefit. But maybe with the state estimation, it would take longer or something like that. But can you clarify that?
Maybe I can elaborate here. So the main intention is that if you are a researcher or analyst or local tester, you want to run something maybe in a Jupyter notebook or whatever, and if you maybe you can switch to the Cartesian product slice. So if you want to test with some Cartesian product and you make some mistake, and then it can grow very exponentially, and then your Jupyter notebook can just freeze there because it's calculating, I don't know, for 10 minutes if you just put too many dimensions. Now the only way to terminate it is just to terminate the whole Jupyter notebook, and then you can restart it. The question here is that would you like to have a function to terminate only that cell block? Or can you live with that if I made this mistake, I just terminate the whole Jupyter notebook? The reason we want to ask, because implementing this costs a lot of effort to do that. So we want to understand from the community if this is really needed.
Well, you can always reach out later if you have any comments about this. But also maybe any other question about any of the features, or yes, Tony?
Maybe you can also elaborate just here if people have some dimensions on the Cartesian product, like topology change and time series load flow, how should they order the dimensions?
Yes, all right. So as you can see here, I've ordered the 2 updates in a very specific way, and it's actually contrary of the coding snippet over here. And as you can see, the first update involves a change in the topology, right? Because we're disconnecting lines. So we want to avoid to have as many, or we want to have as few changes in topology as possible, because rebuilding the topology is one of the most expensive steps. So if you want to have this as performant as possible, you have to, quote unquote, shift left. You see that we've put first the updates that include topology changes, then they happen the least amount of times. So that's one recommendation. Of course, the documentation has all the details on how can you exploit this, or how can you do this the best possible way. Yes, so there's a question, Francisca.
Yes. Yeah, my question is about this one?
Yes, it's on.
My question is about the merging links into nodes.
Yes.
Is it the plan that this is something that happens internally when I call a power flow calculation, or would it be optional? Could I tell PGM, please use this feature, or please don't use this feature?
So this will happen completely internal, so nothing will change with the user. You can still specify links, and you will still get the output you now get for links. Absolutely nothing should change for you. The benefit you'll get is that you'll get less sparse matrix errors because we remove some of the instabilities that are generated because of links. So from the user perspective, nothing should change.
Thank you.
So on the same topic, I also have a question, because I think you also mentioned there will be breaking changes because of this.
Yes.
And that's related to like the sensors on nodes. And also you mentioned something about serialization functions.
Yes.
Could you elaborate a little bit on that?
Yes. So the serialization functions are some old serialization functions that we had marked deprecated on the Python API. So you can still do serialization and deserialization. Those are the original ones, let's call it. And they are not related to this, but we have marked them deprecated for a couple of years now. So now that we're thinking about doing a major version bump, we may as well remove them. Now, the thing about having this super node kind of thing is that if you have sensors on nodes, it makes it more complicated. However, power sensors or nodes are artificial, or not something you would encounter, but were created to satisfy some use case, to make the life of the users easier. But so far, the feedback we have gotten is that it is okay if we remove them because they are not practically necessary. So that is the reason we have to remove them.
Thank you.
Thank you, Santiago. We're through our time, so let's give it up for Santiago. And then I'll have to skip through some slides again. And in the meantime, I would like to introduce Jaap Schooten, Thijs Baayen, and Nitish Barambe. They will walk you through the highlights of Power Grid Model DS. And later on, Nitish will also stay to talk about how to contribute to any of the projects.
I'll turn it off. Now it's on, right? Not yet. Not yet. Can I break it?
All right, there you go.
Thank you. There we go. Thank you, Peter. So we'll be doing the talk on PGM-DS and going through a little bit of how we use it within Alliander. Let's start a little bit with how we came here. So I think it's really cool that we're now, for the second year running, part of the actual PGM Meetup with the Data Science project. It's a project we started internally, I think, 5 years ago between some teams within Alliander with the goal to actually use the Power Grid model in different production applications. And what we saw is that if we do that, there's not only, of course, the great calculation features you already provide that are very useful, but it's also very practical to have some general helper functions and some structure to work with Power Grid model data. So we started this project with the goal to provide those to more teams than just ourselves, and to be able to work together, improve the user experience of working with Python software on Power Grid models. And that has resulted in this project, and I think it's really cool that that it's now even open source, and we got the trust from the PGM team to add it to the project. And it provides a lot of things in working with the grid, provides graph interfaces, filtering options, and also since the last year visualization, which has been highly requested. And we'll show you how that actually helps our daily lives a lot through a little bit of a use case demonstration. And we'll start with explaining a little bit how the model works, and I'll hand over to Thijs for that, and then I'll get back later.
Yes, thank you. So just as a recap for those who are not really familiar with it, the Power Grid Model DS library is a wrapper around the Power Grid model core calculation calculation library, and we are making, within the library, we represent a grid in two ways. We have a graph representation, which you can see a visualization of on the left, and we have the NumPy representation that you are familiar with from the Power Grid model project, but also we added some extra features around that by combining everything into a grid object. And by having both of these representations, we can ask different questions and solve also different kind of solutions. So also in our demo in a little bit, we will not really go into the integration with the power flow, but we'll show what else you can do with this this extension library. On the left, the graph representation is a RESTwork-X representation. It's a library. It's for those of you familiar with NetworkX, which is a familiar graph library in Python. This one is a rewrite of NetworkX, which is written in Python, and this one is written with a REST core, so it's a bit much quicker. And on the right side, you see the array representation is still NumPy. And here you see the whole grid object, or at least some kind of representation of it. So it's a class, and it has all kinds of arrays and a graph representation of it. But we'll dive into this more later on. So we have a set of new things, and in our demo we'll go over both new and older things, so you get a good overview. Last year we added merges, showing differences, and how to easily rebuild the grid. And we also are now completely compatible with PGM in terms of components. So before we were missing some components, but now we are always up to date. We're up to sync. And we are now also able to serialize the grid. Before we were working with pickle objects, but that has some issues. So now we're able to serialize to JSON and also restore from that. And then we added some other features like extra API methods and stuff to further help you when you're working on a project. And the visualizer has also been had been started last year, and it's also much improved. Also mainly thanks to Nitish. And Nitish will show you more on that later on. But let's now turn to our demo. So we'll do a little bit of role play. Jaap and I are we'll do a fictional study where to show you how you can use PGM-DS in day-to-day life work day at, for example, Alliander. To show you how we use it, and also how it can be really useful for debugging certain data things. So I'm part of team 2, and Jaap is part of team 1. And Jaap's team is responsible for providing data sets. For example, of each substation that Alliander maintains. We have about 180 substations as Alliander. And so you can imagine Jaap will provide my team every day with the latest update of each substation. He provides a grid. And then my team is actually responsible for a n-1 check. So whenever, for example, a cable fails, we at Alliander, we want to still be able to provide all the clients power through a reconfiguration of the network. So in this fictional example, we want my team is responsible for doing a daily n-1 check on all grids at Alliander. And so in this case, we'll encounter a bug. My team will encounter a bug, and I'll talk you through how we then hand over the data to Jaap's team, so they can investigate the bug. First, I'll tell you a little bit like a code example what my team has done. So we're using the Power Grid Model DS to build a specific grid, and this is really common with teams that use Power Grid Model DS. So we have in the first row of the import, it imports the standard grid from Power Grid Model DS, and that grid contains all the typical components that you would find in the in the Power Grid model core. So you can see it on the lower part here. Inherited is the line, the transformer, the sim load, and all other arrays from a PGM. And then from PGM-DS, you also get a graph interface because that's the graph representation. And one cool thing, at least what I think, and a really useful thing that you can do with PGM-DS is extend some of those arrays, so to add some extra information. So, for example, here we have extended the node array to save some extra information on nodes. So normally you get from the node array the data model of PGM. You get at least an ID and a U-rated value as an input value to the, for example, the power flow. But from PGM-DS, we also add a node type and a feeder branch and feeder node IDs to support some extra features. But in this case, you can also always add your own column or extra field on the array to store some extra information. So in this case, we've added a field called backup node, and I'll clarify in the next slides what it's about. But this is an extra field that for each node we can store that information as well as an integer. And then this is our simplified function of what we do every day. And it will highlight some of the features of PGM-DS. So we'll just go slowly over it. This function accepts the grid. So that's the grid that we just saw on the previous slide that contains all our assets. And it checks, like you can imagine, like we do for every line in each grid. So we have 180 grid. We try to see if we would mark this line as faulted. So if it would fail, can we still find a backup route for all the nodes in the grid? So that's what we do in this function. And yeah, as you see here, it's a simplified case because here we are only going to check whether there's a topological backup for the faulted line. We're not going to do any power flow calculations in that. Normally you would, but that's yeah, that's for a real implementation. This is for the simplified case. So to go over each thing. So let's go over the basic structure first. We're going to remove the faulted line from the active topologies from the grid. So that's in the graph representation. And then we use a graph query to see where we can find another path to a feeder node. So that's that one that provides power. And if so, we're happy. And if not, we raise the no backup route found on the bottom. So let's go over it one by one. First, we get the node ID of the affected node from the faulted line. So we consider that, in this case, always the 2 node of that line. And you have an upstream node that is above that line, which is where the power is now coming from. And we also collect some substation IDs. So these are bus bars. These are nodes within the substation from the buses within the substation, which can provide power. And our first step is to inactivate that line. So then we simulate that it would fail, for example. And then we use this at step 2. We start a new temporary with a with statement. We create a new scenario where we use the temp remove nodes method on the graph to temporarily remove the upstream node. So it's not part of the graph anymore. And then we loop over all the substation IDs, so all the other substation nodes, bus bars, to see whether we can find a shortest path. So you see that on the line, I can actually point it out, I think, right, if it works. Yeah, so in the complete graph, we can see whether we can find a different path from the affected node to that substation ID. And we try it for all the substation IDs. And if we find a path, then it gives a return. And we can update the node. And this is where our substation node extended field comes into play. That's why we store that as a extra, store that data at in the node array, and then return the path. And we try this for every substation node, but can be that we cannot find it for a substation node. We go to the next one if we cannot find the node. But if we tried all the substation nodes and the list is exhausted and we haven't found it in any of those, then we raise this error, so no backup route found. So in this fictional example, let's say like for yesterday, all was good. We had 180 grids that were all the lines in there were n-1 compatible. But now today I get on a specific grid, I get an error, and probably something has changed in the topology. So then, yeah, I have an error, and then I turn to Team Jaap, data pipeline. So hey, I've loaded these data sets, and now I have a failure. So how do I? How can you help me out? Find out how that works. What could be the issue? So Jaap can reply. Please send me the serialized inputs, and then Jaap can investigate the error. So I'll hand it over to you.
From here then, thank you. So I think also really, let me get the clicker. Really nice to see that, for example, in the like it's a toy example, of course, the fault line function, but it really takes just a very small amount of code to build like an advanced feature without having to do all the bookkeeping and complex things on managing the grid, and helps you as a developer focus on really building more advanced algorithms instead of building code to support that. So that's what we aim to do. And then, of course, there's a lot of times we're working between teams, and then some question pops up, and you want to be able to share data and investigate what's going on. So in the past year, we've worked on the serialization functions to be able to save a grid to JSON and then load it into the a new type of grid in another team without having to fully have the stack supported from the other team. So for example, you saw that Thijs' team had made an extension on the grid with all kinds of extra nodes. Me and the data team doesn't have that extension, but with the serialization function, we're able to share the full data of his network and still able to load that really easily into my investigation notebook I'm going to make in the data team. And it's actually really helpful to be able to share data between teams or between users and us as maintainers of the package. So this example really showcases that daily workflow we have. Even last week, I helped some teams with debugging, and then the first thing I always do is get the data, of course, like Thijs said, and then start looking into what did I receive from the other team. So one of the things that's now even more easy is get first an impression of what is contained in the grid of this other team. So we added the wrapper function, which prints actually now something that's really useful in first investigating what has this team been doing. So I can see here that this network contains 8 nodes. It's a toy example, it's very small, but you can see what type of data am I working with. The team has been adding nodes, transformers, and lines. But there's, of course, a lot of more components you could add. And that first overview you get now is what is contained in the grid, which columns are being filled with which kind of data. Is there something weird in that? And often this really already helps in finding what's going on. Did I miss something? Did I forget to set, for example, an ID column? Is it empty? Then I know the problem is going to be there. Well, in this case, this looks all fine. So the next step is that we use the visualization. And that really helps in searching through what kind of situation am I looking at. In this case, we've got a small grid, and I need this one. You see here in the diamond shapes, this is a visualization of where the substation is at. And then we have some lines pointing downwards going to the nodes of this substation. And similarly on the other side, so in this toy grid, there's 6 nodes and 2 substations. Yeah, and here on the top you see also where the sources are. So Nitish will go into all the nice things he's been adding. So you can get more and more details of how your grid looks. And seeing the bug we saw, that there's no backup route if something fails on this side, and that actually is correct looking from the data. So there's no way if this line at the one substation fails to be able to connect to the other substation. So it's really, when you see what is in your data, it's really easy to find out what's going on, of course. So let's see how that might occur from us in the data team. So what's the way of working on loading the data is that often data lives in different data sets for each substation. So you have a substation on the left and substation on the right, and they all live in different files or are loaded different in different processes in your data processing. So to help support that, what we've been adding in this year is merging different grid objects, so you can work on them parallel, load from different files, and then merge them together. So you see here an example of how that works on a really simple grid. We have some different modes we support to be able to specify how you want to handle the IDs in the different grids. If you want to keep IDs from one grid in the other, or you want to recalculate IDs on the new grid to be able to make sure they're unique. But in this case, that has resulted in a little bit of a problem. So the team now knows the problem is that there's no connecting cables between the two grids. So working in the code to see what's going on, we find that if we change, there we are back. That if we now also include the connecting cables, these were missing in the merge actions we did. And it's really has been helped by visualization and exploring the grid object. So now we found really easy by the new features in PGM-DS what's actually going on. And then we can actually validate that by the new difference function. So having two different grids, we can now also print the difference, which can be useful in debugging or also in testing cases. If you want to find out what's the difference in a test between different workflows, we can now support that you let PGM-DS handle that as well. And here in this case, the new merge function we made compared to the data we received from Thijs' team shows that we're missing some cables, which has helped us solve the problem from Thijs' team really easily without having to go into their stack and install software from their side. So those are really features that we've been adding based on what our experience has been within the teams working together, and adding some things from really the use cases we're seeing. And I think that's really how the project has grown. And I hope to also be able to keep adding, of course, based on all the use cases you will be providing in the next year, new ideas that are well helpful and quite useful for us as developers. So that's going through the example. We saw how you can use filtering, how you can use the graph model, how PGM-DS helps exploring the data you have, the visualization, which we'll show a little bit more of, and all the utility functions around that. And then this example is of course a little bit smaller, but we've also worked on a workshop, which we have done several times now already with some at some events, which you can also find and go through a little bit more advanced feature if you want to explore more for yourself how to use PGM-DS in real use cases. So we've got two workshops, one that's really introductory to how the API works, and one that is a little bit more advanced that shows you how to solve an overload in the grid. Yeah, I encourage you to try those. And then we'll go to the visualization with Nitish.
Okay. So right now we have a visualizer in PGM-DS project. You simply have to call it using the visualize function, and it opens up a web page and displays nodes, branches, and all of the graph that is associated with it. So we started as a prototype last year, and now we've transformed into a full feature-rich tool. And the main goal of this addition was to basically be able to view all of the data that you will be simulating, as well as the results that you will get from it. So in this video, you can see how if we click at either one of the nodes or of the branches, you'll see all of the loads, generators, sensors, as well as the node-related data in a tabulated form. Connected to a particular element will be visible down there. Oh, okay. Pressed it twice. So next, okay, more problems. Yeah, it's also possible to do a multi-selection. Basically, you can control plus click on each of the elements, and you can also draw a box of selection. And what happens is that all of the elements that are associated with those specific elements would get displayed in the tables below. So anything that is connected to those two nodes here, for example, will be displayed in the tables. And this is quite useful because in this table, you can have conditional filtering based on different attributes, and many different data exploration possibilities can happen with the tables. Along with that, you can also plot now all of the batch data within the calculation. So just like in the previous video where you clicked on a node and then found out the table, now you can also click on the respective cell of the attribute as well as the ID, and then you can see a graph below as to how that ID component and the attribute behaves throughout the scenarios. So it can be either, in this case, voltage results, or in the next case, in energized results, as in if something is active or not active after a state estimation or a power flow. So to do this, you simply have to add update data and output data as keyword arguments to the visualize function, and it's that easy. It can plot all of the attributes that are possible. So basically, we can add way more functionalities to the visualizer. It really depends on what the user wants, because these features as well as styling related things are very user specific. If you have some opinion or if you have some ideas on this, please drop a issue in the GitHub board of PGM-DS project. Okay, that's all for the visualizer. And yeah, back to you.
Thank you. I'll finish it off. And really nice you added the videos to be able to still have a little bit of a real interactive showcase. Very nice. So what are we going to do next year or hope to work on? So like I said, we aim to really add features based on what developers need. So we're really open to contributors and also you making issues with features you would actually really like. And that drives our roadmap mainly. Based on that, the 3 topics we mainly are aiming to work on is improving developer experience. So working also on the typing improvement and ease of use of the package. Then the visualization is something that there's still a lot of ideas on how we can improve that. And there's, I think, a lot of room to be add new features. And the last thing that we're investigating on extending is the graph interface. You saw in the demo from Thijs that, for example, we have support for main functions like the get shortest path. And we would like also to be able to extend the graph interface to let users do more advanced algorithmic analysis themselves. So now we mainly provide functions from WestworkX through the graph interface, and we want to extend that also to be able to let you build a little bit more graph searching kind of algorithms. And then I hope to see also a lot of contributions from you guys. In the last year, we've also seen a lot of new people, like you saw in the graph from Santiago. So that's also really nice. Then some other things we're doing is that we're dropping some minor deprecated functions already at the moment. So for example, like the pickle interface, where now we replace that by the JSON serialization. We've been marking that deprecated for a while now, so we'll remove those in the coming months. And then at the meetups or at the online meetups, we would also like to discuss on some more major API changes and see how the community wants to handle those. So we're now supporting, for example, dot notation in the arrays, which I think on the one hand is really intuitive and provides auto-completion. On the other hand, it makes it more difficult to do type hinting. So we would like also to discuss with the broader community how we would like to handle those, which is more important to us. And if we want to change that, that would be a major change, I think. So we would really work towards a 2.0 release. And then the other thing we're really open to at the moment is that I think we're already providing a really nice basis of working with the grid and let other people implement algorithms. And the next thing we would be more open to is also provide more experimental modules in which we provide more advanced algorithms to the user. So now that's not something included in the package, so there's no optimization or, for example, how to connect the customer to the grid. That's not something that's provided, but you can do really easily with the package. But it's still something we hear from a lot of users that they're doing. So if we can find a way to provide utility functions or help in that to more experimental module, that's something we would also like to do in the coming year. And of course, very open to all the ideas from the community. So I think that was it for the PGM-DS, and then Nitish will finish off on helping you how to contribute.
Yes. So, how can you now contribute to the Power Grid model ecosystem if you wish? The best thing you can do is you can use the library. You can use it with your own data. You can develop an application with it. And the real world usage is very valuable to us. And you can share feedback or any bug reports. And it can also help us identify any edge cases that are involved and any places where we can improve. The usage is one way. Then you can also contribute to the validation test cases that we have. So that so these validation test cases help the models stay correct and stable as the project evolves through different versions and with newer features. That also is possible to do. And then you can provide improvements to the user as well as the developer experience. So this includes APIs, tooling, code quality, testing, documentation, a lot of such places. And if you're more on the theoretical side, you can share mathematical derivations and electrical models about either electrical components or over the calculation features. So just research level stuff that we can then translate to code within any of the repositories. So depending on these tasks, the final code would actually live in PGM, PGM-DS, or PGM-IO, depending on what it is. So new calculation features go in PGM, grid manipulation, array, graphs, etc. go into PGM-DS, and with PGM-IO, you can share conversions from new data formats to and from PGM. And how to do the actual contribution is present in this link. It's quite detailed, and it should cover all of the doubts that you would come across it. So it's also present in our documentation. It follows all of the process of making a fork, what are the code quality things that needs to be complied, all of the other helping tools that can guide you through the contributing. Yeah, you can visit that. And again, for smaller issues, maybe you can do it yourself. But if you feel like you need help for any of the larger issues, please don't hesitate to contact either the community or all of the maintainers involved. It's always nice to align on all of the efforts as well as the design that's possible for those features. And then if you're new to contributing with code or with the project, you can have a look at the Good First issues in all of our repositories. So this is an extra label that is visible in the issue board. So these are smaller tasks that help you get familiar with the code base and the contribution process. And if you have any other questions about it, you can, of course, first of all, create an issue in the issue board. You can put it in the discussions page of the Power Grid model project if you don't find a special place to ask your question. And then you can talk to any of the maintainers here today or in the community meeting that occurs, or you can just send us a mail. That also works. We try to be very responsive and accessible to the community, because that is in fact one of the nicest feedbacks that we received, that PGM is one of the few open source projects that actually respond, and we try to maintain that. We usually respond to all of the questions really fast. Let's see. And yeah, finally, you can contribute to any of the engineering, research, or software side, anything that you're comfortable with. We would really like to build this together, build the project together, with everyone. That's all from me. Back to Peter.
We have 2 or 3 more minutes until the next presentation. So if there are any questions either to Nitish or Jaap or Thijs, then we do have room for that. I see a question in the room.
I'm Ankur Arohi from Emsys Grid Services. My question is regarding the application side of it.
Can you put it a bit closer?
Yeah, my question is regarding the application side of it. So imagine sitting in an operations room and you have an active fault there is no time of sending deserialized and serialized objects around and then talking about which line to connect, what are the mechanisms to deal with that. So I just wanted to know if there is some idea on the application side of it. How can this be actually used? Thank you.
So indeed, asking things is not very, like, we cannot really respond like instantaneously, but we usually respond within a week or so. So not on the direct operations level, but on the back when you're testing, at that time, it's really possible to approach this. And at other times, it's also possible to use the grid manipulation tools and visualizer, etc., to figure things out. And I see Thijs has more points.
I wanted to check whether you were asking whether you have, when you have questions, then what the response rate is, or whether it's about the serialization that we were talking about.
I'm asking about a real grid scenario where you really have a fault and you want to see if there are topological switching changes that can help.
Yeah, so then it's about, so you're saying like if you're in a real grid scenario, you might not have the time to serialize the data and send it to another team. Yeah, I think it depends on the project. Like the projects we're building, it's more like long-term strategy. So you have a little bit more time to debug your stuff. If it's like operations system, it's all like automatable. You could build your own custom software to maybe automatically send it over. But yeah, this is not natively supported from within the project at this moment. But we can talk about it later.
All right, room for one more question, if there is any. And if not, then please give one warm applause again to all the maintainers. And then we're done with the most technical part of the day. So we'll be jumping into our use case presentations. So our next use case presentation is forward-looking bottom-up grid state forecasting and optimization using plug-and-play software stack. So I'd like to welcome Ankur Arohi from Emsys.
So, am I audible? Yeah.
There's a clicker.
Thank you. So, good morning, everyone. Thanks a lot to, first of all the hosts and the PGM community. It's really nice to be here. I would be talking a bit about the application side of the tools. So, as we know, at the landscape of open source, we have at this moment a lot of good tools, a lot of good ideas. But then the question comes, considering the problems that the electrical infrastructure is currently facing, problem of reliability, security, how can we translate the open source landscape from research to application? That's what we are trying to do at Emsys Grid Services. We are a company which is pretty close to Groningen in the north, on the German side. And what I'm actually trying to convey is the aspect of grid being not full, because the current discussions regarding the electric grid is really full. So by full, people mean we have at one side a lot of renewable generation. So the hosting capacity of the grid is reducing day by day. On the other side, we have huge data centers, huge loads, gigawatt of loads being planned. So on one side, we talk about intermittency of generation. On the other side, there is intermittency also at some aspects of large load. So this concept of kind of balancing between a lot of intermittency and a lot of load is what our company is trying to fill in. So what we are actually trying to do is to see how can we fill the gap between planning, grid planning, and grid operations. Meaning, let's take a scenario. There is a specific substation which the planners planned considering worst case scenario. That's how it is done. So you go, you get in the long-term planning studies. That's incorporating a lot of calculations, even more versatile than Monte Carlo simulation because you run a lot of scenarios. And then what you try to actually answer is, how can we reliably provide the power to a specific node without facing the issues of balancing? So basically resource adequacy. But then, if you go on the operations sides of the grid, you would see that most of these scenarios, the worst case scenarios, are actually not true. So the transmission capacity can be increased if we look at the operations with optimism. And we want to see how can we tap into that. So just a small introduction of what we do. We are a conglomerate of 3 companies. We actually come from forecasting. We started forecasting in 2004. So it was all about asset forecasting. You talk about wind and solar. And now we have around 200 customers where we actively integrate these forecasts and their renewable portfolio. So the 3 companies are Emsys Grid Services, the Meteor Systems, and VPP. The VPP solution mainly deals with the controlling and virtualized operations of the portfolio of our customers. The Meteor Systems is providing physics-based forecasting of assets. And where I actually come from is this aspect. So what we do is we integrate those forecasts, integrate loads of different solutions available, and try to see how we can develop solutions that actually help grid operators using not only open source, also proprietary software, but mostly open source. So the one thing that I want to really convey is that infrastructure takes years, but the operations, and by operations I mean the grid operations, they really have to adapt now. So it takes around max 2 years to build a data center like this, which is pretty good. But then it takes more than 3 years, up to a decade, to actually build in a new substation, to actually buy the things that they really need, to run the test, and so on and so forth. So are we able to catch up with the speed of data center, which would definitely exponentially grow in the coming years? That's the question we want to answer. So the data center developers, they are actually looking at the speed, but obviously the utilities, they're concerned about reliability and certainty. Now, the headroom that we are talking about, okay, sorry, just a second. Yeah, there is headroom. Now, what does headroom mean? Headroom means hosting capacity, but translated towards operations, meaning how much more capacity of lines and equipments can I tap in to provide more transmission or more distribution of power. And that's where we are currently in. So at one side, we have so much interconnection going on, especially if we move towards south of Europe and in USA. On the other side, especially in Germany, for example, we don't have any nuclear plants, so we don't have that base load resource adequacy anymore. So we are, on one side, really intermittent, and on the other side, the interconnection is increasing and increasing. So the situations about the worst case scenarios are not fitting in anymore, and if we continue like this, it is pretty much clear that it's really difficult to integrate more and more distributed energy resource and loads. So the high penetration of renewables on the other side is also adding to the uncertainty that the grid is already facing. These are the aspects that we are actually looking at. So one of the solutions that we are actually providing since 2021 is proactive congestion management. So what does it mean being proactive, and why proactive? So the distribution system has really done a great job to come up from a system which actually passively somehow managed this or was always over-dimensioned to a space now where we are moving into the scenario that the distribution system is actually pushing in the transmission network, which is pretty good. And that's why there is a need of proactive congestion management, because the DERs that are exponentially increasing at the distribution level are creating a lot of concerns about reliability and congestion management, not only at the distribution level, but also at the transmission level. So these are a lot of questions. I just put them here to show you how can we integrate tools like PGM and others to solve some very specific industrial problem. Now let us look at the first question. We have uncertainty of production, meaning we always have good wind forecasts, but nobody guarantees us that the wind forecast is exactly like a diesel generator or a gas generator. Nobody can say that because there is always certain amount of uncertainty of weather conditions, uncertainty of not expected events, and that's where we are. So how and where do we know the uncertainty is physically accumulating? At which node? At what time? And if this uncertainty increases a level that there are issues, there could also be blackouts. So the question is, do we actually know at which node level before operations actually pitch in? So I mean, after day ahead till the operation, or the real time, we must somehow know which nodes are uncertain, which nodes are creating problems or would create problems in balancing. At what substation? So it was a very nice talk about the substation topological aspects. That's one of the aspects that we are looking at as well. That's why the question about usability, because that's where the intelligence is at this moment, or that's where the industry is going in at this moment, because the substation is the aspect or the physical layer. If this is controlled properly, we have good chances of not having big issues in the operations. That's where also LF Energy CPath is going. That's where the virtualized protection and control groups are working on to make substation intelligent enough so that the substation understands that after day ahead, the wind power was, let's say, 5 megawatts. At this moment, for some reason, the wind power is 10 megawatts. So instead of centrally curtailing this wind power, I can do something on my own, or like a peak shifting. That's the aspect of demand response which makes substation a very important aspect of how grid is being operated also now. So ABB released last year an intelligent substation module where everything is completely virtualized. It's already in operation, and there are certain rules which this intelligent layer at the substation follows in order to do peak shifting. And this is amazing because now the grid operator can say, I know this substation is pretty good because we have a solution that works, that is running from day ahead, intraday to real time. So without going in much details of the other aspects, I would like to present something else, which is our tool currently also operationalized since 2022. It is a microservice infrastructure, a web interface and data exchange services platform that runs on Kubernetes and can be deployed in client solution. What it actually does is, I will speak a bit more in detail about which open source tools and how we integrate them. So we have made an integration layer of different solutions that runs at one space, and it does different kind of stuff. So that's where we, as I was saying, we originate from, basically asset forecasting. So you can see all of your assets nicely in the dashboard, their forecast, their uncertainty values, and stuff like that. Now, this is where our intelligence comes in. What we do is we do vertical network load aggregation. So what is a network load? If you talk to a power flow engineer, person who is really doing balancing and operations, everything is about net load forecast, because that's what matters. That's the thing that has to be balanced from substation up to the zonal level and to the whole network level. So the vertical network load aggregation is an object that we have created, an intelligent object that aggregates all the DERs below in day ahead and also before day ahead, including their forecast, taking in telemetry values from the substation, taking in historical values, and creates net load forecast. So the operator doesn't have to go down to the medium voltage network or even low voltage network behind the meter to see what are the outputs of a small generator or a DER resource, but the aggregation layer reduces much of this complexity. And this aggregation is done in a grid-aware sense, meaning we respect the grid constraints. We see what is the PDDF value. We run a lot of simulations before. So that's about that. And the third aspect that actually uses vertical network load aggregation as input is nothing but a co-optimization module. This is the intelligence layer that sits between an aggregated point and at the zonal level. So meaning that we try to see if there are possibilities of switching, but that also before actually it happens. So we already catch in the things, saying that if that happens, you can do this. That was the aspect. And the second thing what we see is if we can run demand response schemes. So these are some remedial actions which could already be pre-planned so that the distribution operator is feeling much comfortable, because there are many aspects which already the demand response looks at using the forecast and also reduces the peak shift. Actually does the peak shifting. Now there are some advanced aspects that we are looking at. So as I was talking about large load, that's a big thing in the USA at this moment, because the large load integration, considering the data center aspects, is enormous. And so we are trying to see at the hosting capacity enhancement using flexible connection agreements. I will talk about that in a while. So the question that we are trying to answer is, how can we increase the hosting capacity considering the current forecast, the forecast for the whole year, and what would that mean for the units which are below? Can we run them flexibly? Then this is about the dynamic line rating. That means considering the seasonal forecasting of multiple aspects, can we somehow say that the transmission line or the distribution line is cooled to such a level that we can transmit more power? That's about that. And yeah, the aspect that we are actually currently researching and trying to come up with is something called probabilistic forecasting, meaning in the operation side of it, how sure can we be that the grid which would be operated in the coming 2 hours is reliable enough? So we try to see what would happen in a case of a storm, or in a case where multiple units are simply not working, which has already happened in the past, to see what is really, really the worst case, which is not planning worst case. This is the worst case in operations because there are differences, and that's what this tackles. We talked about topological optimization, and what this platform actually does pretty good is it has a direct API connection with the utility. That means it has a connection directly with DSO, and through that also to the DSO in Germany, and we share every second information, what we calculate and what we get, for example, for telemetry and so on and so forth with the utility. Obviously, we don't have GoPax yet. Folks at Alliander know what GoPax is. So it's, you guys know better than me. It's about the, it's a platform that Alliander, together with Tenet and all the other DSOs in Netherlands, created, which provides flexibility going from day ahead to real time to solve issues of balancing in real time. That's what people do when there is uncertainty. You actually go across and look for fast ramping solutions. So you say, oh, I have a problem and I can solve it if I use this flexibility at this rate. And all of that you can find in GoPax. That's a platform. So that's what the platform can do. It can, through the API connection, also look for flexibility. What we do in Germany is there's an entity called Einsatzverantwortlich. That's a German word which says, which refers to an entity that is owner of aggregator, and they can provide flexibility. So that's where we currently have our API connection with. Why is all this important? So in Germany, around in October 2021, there was a mandate about redispatch 2.0, which changed a lot things for the distribution system operator, because every unit that has an installed capacity of 100 kW and above must take part in balancing. And that means that there has to be a lot of connection between, and of course, not only connection, but communication between the entities and the grid operator. And that's something that our platform solves and is currently operationally running in that case. Now, there's a very similar thing happening in the USA with the FERC order. So FERC stands for Federal Energy Regulatory Commission, sorry. The order was issued also around this time. And what it tries to say is every aggregator, which aggregates multiple distributed resources and has an installed capacity through aggregation, more than 100 kilowatts, so you see these both are same, should actively take part in wholesale market. Wholesale market means you pitch in how much you can bid, how much power you can provide in the real time already before, so that the people can plan and operate. So that means both of these aspects already shows the direction where the industry is moving, meaning you need much more support from the distribution side. It has to be much more intelligent, it has to be automated, and everything from uncertainty to operation should be done in a very short window. That already calls for bottom-up aggregation. That's why bottom-up is so important for our platform, because through bottom-up, you already provide forecasting of how the distribution network would behave to the TSO. So how does that look like? Let's talk about a substation. This is a substation, and we have, let's say this is a substation at the medium voltage level, and we have a lot of distributed aggregations that could also be behind the meter below that. So what we do is we use PDF calculation, so that's power transfer distribution factor, in order to lump all of these as forecasting at the. So this removes the whole problem of too many to one, but with quality. So in the end, we create clusters, and these clusters, through this structure, already take part in the TSO calculation, which is the ahead. Meaning, at the European level, there is a core organization which has all the TSOs, and their mandate is to utilize such aspects after the redispatch 2.0 mandate to make these clusters already work at the TSO level through the balancing. And that's very important. So how we do this? We have real-time measurements with API that I was talking about. We have master data from almost millions of such distributed assets. And we have model updates because they keep updating their models. And through fast corrective feedback that is an outcome of the measurements, we can create something like this. So if you see, this is the intelligence, because you're talking about not one forecast, but you're talking about forecast with confidence interval. So OpenStaff is also actually a tool which probabilistically forecasts the load and assets. But at this moment, what we do here is we integrate the fast corrective feedback that actually corrects, improves the forecasting, also the probabilities, also the confidence intervals, to make them useful for tomorrow, so for the operations. So in the end, it looks like this. We have the uncertainty band. This is something important for us because we run multiple Monte Carlo simulations to understand what would be the real worst case scenario if we use these kind of uncertainty bands. And we have also flexibility provision that we aggregate at the nodal level to see what amount of flexibilities we have at what time. So, and that opens doors to co-optimization, which we are currently planning to do with another open source tool, VeraGrid, and through their optimization engine, we try to solve the peak shifting problem. And these are then planned remedial actions that simply goes to their SCADA system. So what have we done since 2021 using these aspects? Of course, these aspects have been improved via feedbacks from our customers, via problems, via new ideas. But then in the end, around 20% of hosting capacity increase in multiple substation points at the distribution level, because we use something, through that, we inherently do something like that. You have, at this moment, static interconnection everywhere, wherein you say, okay, I have a grid capacity which changes. But normally, people also simply don't use the changing grid capacity, they use a static limit. But let's say we have a changing grid capacity pertaining to the situation, and that would be the maximum allowable connection. But then, if you actually incorporate that, you can have a flexible interconnection, meaning you say, look, I would not curtail you here directly, or I would allow you, even if you have a more installed capacity, to actually get interconnected in the grid. But when the grid capacity, which is itself a dynamic thing considering the forecast, if the grid capacity is not supporting at this particular moment through our forecasting, because we know that before it happens, we would curtail. And the amount of curtailment would also be calculated through our platform. So that's what we have done. Okay, that's what I have tried to mention here. What through this aspect, we can integrate more and more prosumers. So that is also loads and data centers, stating that we have a very good understanding of the whole substation, not only for a seasonal value, that's how it's done mostly now, but for the whole year, and we know what are the edge cases. So how the process flows, as I was mentioning, we have the grid-aware forecast. We also have the uncertainty envelopes. Through that we can co-optimize. We know how to use the flexibilities, and then we have recommendations, which is already done before operations kick in. And then we also utilize the feedback. So I've been told that I have only 5 minutes left, so I will try to be a bit faster. These are a bit details of how we do it. One important key takeaway is that we merge, you're talking about merge, we merge the DSO and the TSO file. So TSO's day-ahead congestion forecast file, CGMES or UCD, is merged with the DSO CGMES, and that runs every 15 minutes for multiple scenarios. And then we do this aspect. So one cannot say, okay, but you're looking at a very small data set. No, we are looking at a huge data set, and that's how the whole function works. Again, details, but in the end, what I want to say from this is, at this point of time, we integrate all of these topological aspects. As you see, it is before T-minus 18 hours. So we try to create the reality before it actually happens. And we run the uncertainty-aware security analysis, the remedial action optimizer, and then in the end, what are the outcomes? The outcome is we can already say what would be the slow ramping flexible products that has to be procured, what is the optimal ramping possible, what pre-dispatch we want, we should have, and the topological optimization. So what are the non-costly solutions? Now coming to the open source part. So as we started the whole thing, our first problem was everything was highly dependent on the quality of input data. So we had issues sometimes in the input data, and the pipeline was not working. So we wanted a system which should be as robust as a USB reader. If one driver is not working, we need to find another one, but we should never, ever crash. And that's what we tried to find out. And our answer was, well, let's tap in the open source. And that's what we did. So before we were only using proprietary tool using Neo4j, which is similar to the graph that the PGM-DS is trying to show or is doing. But then now we have tools like PGM, Possible Power, and VeraGrid that is running in a plug and play strategy, meaning we already know for which network, which tool is best suited, and we use that tool. So for example, for the aspects of merging at this moment, we are using Possible. The commit made pull requests at the Possible level. We are also committers there. So through that, we knew that that's the best. Now, looking at the forecasting, we are already looking at OpenStaff, but we have our own proprietary solution for the forecasting and using uncertainty bands as well. And we are also looking at the topological aspects from the TOOP, which was released last week from 50 Hz and made open source. So this is what I'm talking about. We are at the we are trying to create a platform which is an integrator and tries to look at the open source on one end and the proprietary solutions to solve a particular industry problem. Yeah, and we are also API agnostic, meaning we can run completely stateless, and we could be then completely triggered from a on-premise platform integrator. That's where the TSO at this moment is looking at to run something at their own space. And we could also integrate other solutions, because in the end, what we are running here is a Docker are Docker containers. So because we were dealing with the open source world, we needed something which we call self-healing system, SHS, internally. So this is the problem that we were always facing. CGMS import, forecasting the network, but the CGMS import was breaking. So what we did is we created this. We looked at how can we use Apache Kafka to automate integration of multiple containers running already the open source tools. As you can see, these are standby containers. They are running in parallel. I know there is a problem. I simply know what I can do with the Kafka. I have already set the Kafka in such a way that the solver engine and algorithm changes on the run, but we never crash. So using this situation or using this idea, we tap in multiple tools and we try not to crash, because not one tool cannot solve every problem, and that's where we tapped in. This is how it looks like. I'm already done. So you see the forecasting. This is of actual grid. I have anonymized everything, but then you can see how the forecasting looks like. Which level are we talking about? How is the N-1 contingency analysis looking like? What are the remedial actions we already planned? And how the master data looks like. Well, and this is one outlook that we envision. We say that this could be also very interesting when multiple DSOs take part in such a synchronized platform, and we provide through this optimal solution to the TSO. And that's it. So thank you.
Thank you, Ankur. Unfortunately, there's no room for questions. If you have any questions, please hit them up during lunch, or put your questions in the chat, and we'll make sure to forward those to Ankur. So thank you very much. So now it's time for lunch. We'll all walk to the Skybar, the lunch location, in one group. So please follow the instructions. If needed, it's possible to use the elevator, but else we'll just use the stairs. For the people only attending the morning session, thank you. And we hope to see you again. And for the people online, we'll start in about an hour at 1 p.m. So hope to see you after lunch again. Let's go. All right. Welcome back, everyone. I hope you had a nice lunch. And welcome to the new people. I know there are some people that are only attending the afternoon session. And because there are some people attending the afternoon session, I'll quickly repeat some things that I've already said in the morning. So first of all, I would like to thank Brightcubes and Interconnect for hosting the Power Grid Model Meetup together with us. I'm looking back at a really great morning session with a lot of interesting talks, updates from the maintainers, the first use case presentation. And the afternoon is filled with more use case presentations and some lightning talks and a keynote. But before we get there, safety first, again, same as this morning. So in case of an emergency, please follow the signs of the emergency exit or the instructions of the Interconnect personnel. Don't drive and call for the people online, also not hands-free. The session will be recorded and photographed. And if you're online and want to ask a question, you can put your question in the chat. And there are some moderators here that will ask your question for you. So let me introduce myself for the people that weren't here this morning. I'm Salemink. I'm the chair of the Power Grid Model project. I'm a software engineer and product owner at Alliander, Dutch DSO, which most of you probably know. And I'm also a guest lecturer at the Eindhoven University of Technology, trying to bridging the gap between academia and the industry. So now we'll get to some new slides. Because I also want to tell you something about the project governance, how Power Grid Model is governed. So first of all, we have the technical steering committee that consists of me, Werner van Westering, Tony Xiang, sitting here, Jaap Schooten. There he is. He was sitting on the front row this morning. and Jonas van der Boogaard, and the maintainers of the Power Grid Model and Power Grid Model IO package, Nitish Parambe, Martijn Govers, Jen Wang and Jerry Guo, who can't be here today, and Santiago, who's sitting in the back to answer the questions online. And Power Grid Model DS with Thijs Baayen and Vincent Koppe, that's also not here. And then, of course, we have you, the community, so all the developers, contributors, and anyone that's helping us create a nice package. So nice to see all of you here. We're here today at the Meetup, which you obviously know. And besides getting inspired by all the cool presentations, we also collect input today for the one-year roadmap. So it's a rolling roadmap. It will be updated throughout the year based on community feedback. And then a year from now, we're here again at the Meetup. We reflect on the highlights of the year as we did this morning, and we'll look ahead. So this morning we presented a roadmap as it is right now, but any input that you give us today or in the coming months or the rest of the year will be taken into account to adjust the roadmap along the way. So talking about our roadmap, if you have any ideas, there are already a lot of issues online with new ideas, new features, bugs as well that need to be fixed. But if you have any cool ideas, please post them on the issue board of any of the repositories. Or talk with one of the maintainers today, because this is also your chance to pitch your ideas, discuss. And it has been mentioned already, but we also have the 8 weekly community meeting that I'll also mention at the end of today again for people if you want to subscribe. But that's also the perfect moment to discuss with us. So that said, now we get to the interesting part of the day again, and we'll continue with the keynote, which is called Powering the Energy Transition, Different Pieces, One Shared Puzzle. And it will be given by Martijn Govers from Bright Cubes. He's hired by Alliander as one of the maintainers of the Power Grid Model project. And so please give a warm welcome to Martijn.
Hello, everyone. Before we get into the keynote itself, I would like you to take a moment to have a look around. Look at the people sitting next to you, maybe in front, maybe behind you, for the people joining remotely. Think a little bit about the people you've interacted with over the past half year, or maybe year, or even beyond that, just to do the job that you are doing today. And not necessarily the amount of people, but just a variety of them. Which organizations do they come from? How do they join their efforts together to make you be able to do your own job? That said, let's get into it a little bit. First, I'll start with who I am. Peter already gave me a nice introduction, but obviously there's a little bit more to be told. The energy landscape, I would be very surprised if no one here knows exactly what we're talking about, but still it's good to be on the same page. Then the energy transition on paper. We have talked a lot about different use cases, but why do we even have to do this in the first place? And then what is the variety of things we want to do, we want to solve? And then we'll shift our attention to how we put it into practice, because that is actually where the challenges start. Well, actually resurface. And then I'll also talk a little bit about why the same challenges keep happening over and over again in every single branch, in every single company, in every single party, trying to solve this energy transition. And then I'll also dive a little bit into how we can actually work around that, because we already know the solution to this whole issue. First of all, I'm Martijn Govers. I have a background in physics, but I've been working as a scientific software engineer for the past, well, almost 9 years now. I, as Peter already mentioned, am currently also working for Alliander via Brightcubes. I also have previous experience at Philips and ASML, among others. And I'm also one of the core maintainers of the power grid model. The energy landscape. This should look very familiar to you guys, but basically we have somewhere where we have some power plants that generate some electricity that's generated and transmitted over long distances, nationally, internationally, you name it. And then we have some substation, some distribution to the people. Oh, whoa. Sorry, it's popped up in a very weird location. And then we have our customers, which you are yourself as well, of course, because, I hope that everyone has a house that they can use electricity in. You're your own customer. The energy transition. We have to move towards renewables. We want to move away from fossil fuels. Use the stuff that we have. Use the fact that we have wind. Use the fact that we have ocean. From the sky into mountains, and then from the mountains back into the ocean. And solar panels, of course. We also have higher demands. We have data centers now, as have been mentioned a couple times before. And we also have this increasing grid complexity. Because, circle back 40 years, and power would flow always from the power station to the customer, in one direction. Imagine, putting a sensor into the field 40 years ago. You only have to worry about the magnitude of the current or the power. But, now we have these kind of solar panels. We can't do that anymore. We have to think about power flowing back from the customer to the source. So that increases the grid complexity. We have to do things differently than we did, well, for basically 100 years before this. And then we also have to deal with tight constraints. We're already late. It's already happening. We are time constrained. We are money constrained. We are people constrained. We are resource constrained, like literally putting cables into the ground. We have a shortage of cables. We have a shortage of power transformers. So how can we make this stuff work then? We also run into limitations on each of those situations. The people who were at the Power Grid Model Meetup last year have probably seen this picture multiple times before. For the guys who remember, it's looking a little bit more red than it used to. And that's no good. Even if we only focus our attention to the distribution grid, it's still, well, a lot of red, more than I would like. No good. But what is this capacity we're talking about? Well, we have a very simple supply and demand. If there's a high supply and a high demand, well, then we get high loads. High loads lead to high currents. High currents lead to heat production. Heat production may result in melting of components. You don't want that. You don't want fires. So then you have circuit breakers. But then if those trigger, well, then you do not have power. So we're in kind of this indefinite loop of going back and forth. So, that's one limitation. A little bit more tricky is the voltage, because power flows from high voltage to low voltage. Let's say that we have solar panels in one location. There's the sun here. And then we have an EV parking lot on the other side. And then it's cloudy over there. Power flows from one location to the other, from high to voltage to low voltage. So then we have difference in the voltage in the grid. That's all fine. We can configure our grid to make sure that all those voltages are in the same range. But now, suddenly, that little cloudy you just saw has moved away. Now we have power flowing in the other direction. So all of a sudden, we're not going from high voltage to low voltage. Well, we're still going from high voltage to low voltage, but they have switched, they have swapped. So our nicely configured grid suddenly is not so nicely configured anymore. Again, one of the difficulties that we're having to deal with today. But then, okay, so let's say, what does the high voltage mean? Well, if the voltage is too high, devices may not work. They may break down even. If the voltage is too low, same thing. So that's not great. So what can we do when such, capacity limitations are reached? What can we do to mitigate? We can overload the components. If this cable or this transformer is overloaded for half an hour or maybe an hour for like a couple %, it's probably gonna be fine. It's not gonna break down immediately. So you can make use of that. You have to be very careful though, because it increases wear, decreases lifetime. You may have to replace that component, which we have a shortage on, remember? So you may have to replace it much earlier. You can't go along with this indefinitely. You also don't want to go too far above those limits. So we really have to be careful with what we're doing here, because it's a mitigation. We may still increase our cost in the long time. But hey, at least everyone still got power. The next step could be a brownout. Cut the voltage. That nice little Tokyo tower that we have here. I think that's the Tokyo tower, correct me if I'm wrong. You don't always need this very nice image. It's very pretty when it's lit. But if there's a shortage on power, please don't use it. Please don't highlight it. You don't need it. It's a nice to have. It's not a must have. What is a must have is that those companies working in that same district, all those houses, that they have power. That's what we want in the end. So this is one of the things that you can do. Going beyond that, we have a rolling blackout. For the people who have ever been to South Africa, I've been in this situation before. We know that this was happening. That there were neighborhoods, and then one neighborhood might have power from 12 to 2 maybe, and then another neighborhood may have power from 2 to 4, and the other neighborhood would have a blackout. Temporary blackouts and shift it around. Looks very pretty. I haven't been often in a house where it was normal to have a candle light literally the hallway. But it was also a struggle, because you can't do automatic payment systems. You can't use them. So we knew that. We stocked up on money. But at some point, we wanted to go to the next location. And actually, we were running a little bit low on money. We still had plenty, but not that much anymore. And we knew that we would probably have a little bit trouble finding an ATM in the next location. So we wanted to stock up a little bit more. So we tried. Because we came to the ATM and we didn't have power. That was annoying, but still evening before we had to leave. So let's get back in the morning. We can make this little detour. Next morning, again, no power. Well, tough luck. So then we started driving. There were still like a couple villages before we had to take the long trip and have to be in the gates at our next destination. And maybe those villages would have ATMs. Well, they did. But the first village, again, no power. Second village, no power. And only at the third village that we arrived did we finally find a working ATM. And here's the joke. That rolling window, well, we were driving right in that, because the location where we left off now suddenly had power again for an hour. And we were here trying to find an ATM that didn't work. So, this is the reality, or was the reality. Fortunately, they fixed it for now, but it might pop up there again. Or it might happen here in the Netherlands. And already was quite tricky traveling through it, but imagine living in it. Still better than a full blackout though. Last year, Iberian Peninsula, a little bit of France as well. Was a very interesting situation, but not a situation that I want to have too often over here if I can prevent it. And here's the thing, we're the ones fixing it. We're the ones preventing this. So let's actually do it, no? So how can we prevent this then? Well, we can do what the Netherlands did last month, where basically the province of Utrecht was denied from new connections. I don't know about you, but if you think, if I think about the companies in those locations, or the people, wanting to move house, suddenly can't. Or the companies that want to build a new factory, maybe they've already promised their customers that they would deliver, internationally even. And now all of a sudden they can't open that new factory. It's very impactful. So, this kind of is not an option. If we can prevent it, we should. It's a last resort, but certainly it should not be the solution. So then we can work smarter. And by that I mean, we know, we have a shortage of cables and transformers and people. Let's actually put them into practice where we have to and not just waste them. To do so, you need to understand the grid a little better than we do currently. We can do estimated guesses, but we should be able to do much better with that. We can also do time-dependent contracts. I know some of the people here are working on that, where basically, if you have a bakery and a restaurant next door, that bakery will probably use the power in the morning and the restaurant probably in the afternoon. If you give them both full capacity, you're actually giving them virtual capacity, but they don't use it at the same time. So you can also just combine them, combine those capacity, combine those contracts. And that way you can actually give both of them more capacity. Because the grid doesn't know where the power is coming from. It just knows that it has to transport whatever it has right now through this part of the grid. So this is just semantics. We can do smart charging and flex contracts. If we have those big solar parks, well, if everyone is using the solar parks, if it's a very beautiful day, can you please turn them off? We already are struggling with our capacity, with our transportation. We don't need the power right now. Smart charging as well. You get back from working in your office. You get back home, and the first thing you do is plug that EV into the power grid, and then you start cooking. If you plug that EV in at 8 p.m. or 9 p.m., all of a sudden you don't use this peak capacity. You can distribute it a little bit. And this requires a little bit of governance as well, right? For instance, well, the fact that once your EV is charged, you have to remove it from the power system in most of the Netherlands for most charging stations. That's nice and all, but not if you want to distribute your power. So we need changes in policy, and we also need the software to make this work. We can also do intraday trading. Let the market do its job. Oh, right now we have a surplus of energy. Well, make the energy price negative. Maybe people will actually start putting on that air conditioning. If we have a shortage, well, then let's make it expensive. Maybe people will wait a couple hours with turning on that washing machine. All these things solve a part of the problem, but none of them solve them entirely. So we actually need all of them. And that is actually where the complexity actually starts. Because what we need to deliver, and please bear with me, this is going to be a heavy one. We need to deliver a variety of solutions involving many disciplines in production, at scale, that operate together robustly in many different environments, under ever-changing circumstances, under time constraints, with limited resources. Now, let this sink in for a bit. This seems like an impossible job, right? It may even get depressing for some people. But it doesn't have to be. Because we can break this down a little bit. What we kind of need to do is we need to do a little bit of research, a little bit of electrical engineering, a little bit of mathematics, a little bit of software development, a little bit of integration, automation, project planning, putting the cables into the ground, making new transformers, well, talking to governments. And all of them are their own job. We know how to do that. You know, it's maybe difficult, maybe tedious, but hey, we have smart people in a lot of different locations. We can do this. The real struggle is to combine them, to make them talk with each other, to smoothen this operation. And that is something that we know how to do. Because remember when I asked you to look around a little bit? Well, this is it. This is happening. And the solution, the reason is actually very straightforward. Because many operations, many solutions require the same building blocks, especially so in grid operations. We're geographically distributed. We're not competitors. We're not trying to make each other's life horrible. We're just making our ends meet. We're just trying to make the energy grid actually, well, do what it's supposed to do, delivering energy. And that also means that we're actually building a lot of things in multiple locations, geographically, but even within companies. Well, let's say that there are two companies who both need to do short-term forecasts and grid calculations. Well, they can do closed source development, they can do parallel work, they can both build their own full end-to-end pipeline, or they can combine their resources, make sure that it works well together. Advantages. There is no need to reinvent the wheel. There is no need for double work. Instead, we can just build one robust solution, one robust building block, and then make that integrate with other building blocks. That integration part is important. But we can actually work smarter that way. And open source collaboration is the thing that makes this possible, because it provides this shared platform. It combines everything into shared building blocks. It makes the shared building blocks available to everyone. And it also is a platform for open communication. And that is probably very important here. I mean, it's probably key here. Because if we don't talk to each other in a way that everyone understands and everyone can understand and can read into, then if, I don't know, 2 DSOs in the Netherlands make an agreement, and then a third DSO in Germany comes into play, and wants to use that, well, they don't have to reinvent the wheel. They can just talk to the other people, or maybe even read the documentation that's on there publicly, because we have open communication. So everything is already out in the open. And it fully utilizes the strengths of different teams and organizations. Because we have different teams within our organization, within one company, within multiple companies, that, well, for instance, in our case, we do grid calculations, but there are other companies that also have a team that have to do grid calculations. And then there's another company that also has to do grid calculations, and then another one. That feels like a waste of money, to be honest. So, and probably if we combine our resources, we can both be cheaper, but we can also talk to each other in a better way. We don't have to be experts on everything. We can be experts at what we are good at, and where the need is, where the gap is. And here's the fun part. This doesn't apply just between organizations. How often have you encountered it? That within the same organization, the same thing is built from, from the first line of code, from start to finish, all the way, end to end, 5 or 6 times. It's very depressing, to be honest, to see it. So this kind of train of thought doesn't apply just between organizations and between countries. It even applies within one company. And again, we can actually make this work because the Dutch grid is a little bit different from the German grid. And the German grid is a little bit different from the Luxembourg grid. And the Luxembourg grid is different from the UK grid, from the France grid, from the Pakistani grid, from the Ghana grid. I don't know, you name it. They're all different. But they're different. They have the same laws of physics. So if you make the right level of abstraction, you don't have to reinvent ways to solve those laws of physics. They are just there. They don't change. You might need to think about how to implement things in such a way that you can reuse it. Maybe there are a couple different ways in certain different scenarios. But in the end, they solve the same thing. So let's actually do that, you know? So how does it work in practice then? Nice that I'm talking about this, you know, theory, whatever. But actually what the real world looks like is we have these system operators, which are kind of pillars. They build end-to-end solutions. You know, they just want to make their grid work, to supply energy and to transport energy, to distribute it towards their customers. And they are the grid experts. They are the ones that understand how their grid works, what the quirks are, what the strange little details are that do not apply anywhere else, supposedly. And they also know how their customers behave. What are their strange things? Because for sure, stuff that happens here may not happen in exactly the same way in northern part of Norway, or the same part in the center of the Sahara. But you know, you don't need to know that if you're doing Dutch grid operations, how the customers behave in the Sahara. So they know that, and they can share the knowledge. It's not secret. For sure, privacy is an issue, but not at the level of, you know, millions of customers. And then we have the service providers. The bright cubes, the interconnect. See a couple more people that look like they know what I'm talking about. And they are the ones that host and integrate these solutions. They are not grid experts. They are tooling experts. They are integration experts. So they are actually complementary to whatever the system operators do. And they can also consult on maturation, because you don't want to build something that works today but breaks down tomorrow or next year. You want to build something that at least, at the very minimum, works until we have this next solution that can replace whatever we already have, but preferably longer, you know. And that is the role that service providers have here. The system operators can do that, but like I mentioned, they are the grid experts. They are not necessarily the ones of which their main goal is to do software well. That's complementary, right? I didn't forget about you. The research institutes. They are the ones that invent solutions. They are the topic experts. They know one thing extremely well. And they come up with these new solutions within the energy transition. Maybe new solutions beyond that. Maybe ways on how to collaborate. Maybe, you know, there are people researching how the Linux kernel works. May not be relevant to you, but for sure, whatever you are using now has at some point been improved by whatever has been invented on that area. So they build this knowledge. And then actually I had a very interesting conversation about this very thing earlier today. That, you know, you can write papers and then wait 20 years and then maybe one line of statement that you put in your research paper will be used, probably not in the way that you originally intended it. But we can integrate this. We can do this smarter. Because these open source projects are the thing that provide this platform. They provide building blocks that you can improve. Maybe use one building block into another thing, and you know, and apply one thing that you learned in one place to the other, or learned using one thing in another location. And then those projects are nicely made abstractions, building blocks, that then can in turn be integrated again into those system operators environments with help from the service providers. So this open source project provides also a way to collaborate, because a research project doesn't only make one part of the one system operator's environment better. These building blocks extend beyond that. They also extend beyond service providers. So we can learn from each other. We can get better from each other. I heard Kubernetes being said a little bit earlier. Well, Kubernetes is also being used by a completely different branches. We can learn from each other. And here's the fun part. We're in it right now. Look around you once more. We are doing this open source community. We are doing this platform. We are using this platform. We are being this platform even. PGM is one of those building blocks, right? Because we do have research feature requests, mathematical workouts, contributions coming in. And we do make abstraction of that so that it's easier to reuse it in different environments, in different applications, system operations, grid planning, applied research, multiple more, many more. And then those can also then, in turn, provide their user feedback back into those contributions. And it can be literally as simple as, oh, I spent half an hour trying to find out how this documentation works, because the documentation is not really perfect. Hey, if I had rewritten it in this and this and this way, you know, it would have been better. Well, please do. Please share that. It's that easy to be part of this contribution that makes many other people's lives easier, that probably will also be reading the same documentation and spending the same half hour just to understand what they are talking about. It's that easy. You don't need to build a full application to contribute. So, on that note, I would actually like to combine the things that we've learned so far. The energy transition is hard. There are challenges in every level, in every phase. And the only way to get through this is by getting working, robust solutions in production at scale. And open source collaboration is the stuff that makes this possible, that enables this. Because researchers do create smart solutions that grid operators and energy providers can incorporate and want to incorporate. And IT service providers can help with, by enabling the integration within and across organizations and branches even. And open source projects are the things that reduce this duplication to a minimum by literally being the building blocks, but also provide a platform for collaboration so that this open communication is possible, so that we can actually do this without reinventing the wheel a bazillion times. And then, and only then, do you get better solutions delivered faster. Because everyone holds a piece of the puzzle. And when each team solves their part, then the full picture emerges. And the result is a working solution built faster and built to last. Thank you. Questions?
Thanks very much for the presentation. My question is, I think, a bit far out from the technology, but I would just wanted to hear your dreams maybe about future. if you would need to invent like a team or a department of people managing the electricity grid in this way for the Netherlands, and maybe imagine another one for Europe as well, how many people would you need? Would you guess, hey, this amount of developers and people and scientists we would need to jointly solve this issue and address it?
I think we already have the people we need. We already have I actually mentioned this to Martijn yesterday. We already have all the building blocks, all the ingredients for a working energy transition. You just need to tie them together. So just in that sense, it's just a change of way of work, rather than building a bicycle, or what's the phrase again? Building a baby in 5 days with just more people. It's not the amount of people that are the problem here. It's the way that we try to reinvent the wheel 25 times per project.
Thank you. Yeah, as you know, I fully agree with your story. I have one question: is how do we make it work financially? Because no one minds paying for a wheel, but many organizations are not happy paying for a little part of it, when other people also benefit from it.
Yes, so that ties into this slide. So I did say that many solutions do require the same building blocks, but I also did mention, actually in the slide before this, we're working in parallel. And then if we actually, where was it? Yeah, you can distribute the way of work, or distribute the total amount of work in different ways, right? So you can say, okay, we have two companies that wants to use two building blocks. One builds the first, one builds the other. That's just an agreement that you make. Or maybe you collaborate on both those building blocks. And I think that that's part of the agreements that you arrive upon. And historically, those agreements were made on a, behind closed doors, maybe even, maybe even over dinner. But we can also do it out in the open, because that way you don't have agreements between two companies, but with 25. And then you can solve 25 building blocks rather than just two. So I think this, again, the open communication here is a thing that has prevented the world from working in this way in the past. Hope that answers your question.
Yeah, I maybe wanted to add a little bit to the story, because when we were at the LF Energy Summit earlier in 2025, there was also a presentation a little bit more on the financial side for when you're a company and you want to make money. And I think the takeaway there is that if you involve yourself with the open source solution, then you have something that you can roll out to the 25 DSOs instead of having to cater to each one of them. And if you then become like on the cutting edge with the open source involvement, and that's really a big business case as well. So
exactly, and if you are such a company, you don't have to disclose the thing that makes you money. You can disclose everything that doesn't make you money. That's overhead for you. Maybe that's what, for instance, Microsoft does. The STL, I found a bug yesterday. That's fine, it happens. But, if I find a bug, it's way easier for them so that they don't have to literally have more testers to find those bugs that they probably don't find because they are not using the exact specific pipeline that we are using. So it's either shooting and hoping that you hit a target, or people having a target to shoot on, and when you encounter issues, then report them. And that, I think, applies to companies selling products as well. It's overhead to them.
I had a question regarding organizational change. So we discussed multiple building blocks being, or building blocks rather being built multiple times. So do you have any more thoughts about how you can steer an organization the right way to go, okay, but we already have this, or we could collaborate more? Because I think that's one of the real challenges here, even within a single organization. How do you get heads aligned in that respect?
Yeah, I think that requires a bottom-up approach, in the sense that, you know, if some high boss says, no, I don't want to invest in this particular thing, but then that high boss has customers in maybe within the same company even, and then, I mean, we can do a couple things, right? We can be that person that is being paid in a certain way and talk to their customers. They hear their complaints and then they report those complaints up. Well, then you don't get more money. But if those other customers start complaining via their bosses and, you know, make them talk amongst each other, well, then you can actually get this change to happen. Because if the people that make this kind of top-down decisions don't feel the pain or don't hear about the pain, don't know about the pain, well, then why would they put more money into it? And then even if you are one of those customers, you can also, in the same train of thought, contribute those things. If you have a solution, you already know what you need. If you contribute it back to the original project that you're, well, struggling with, you also solve your own problems, but you also solve it for someone else who then has to spend less time talking to their product owners and beyond to get more money to solve their part, which may actually be the same problem. So I think it works on two ways.
That's also what we see in collaboration. Sorry, that was not on. That's also what we see in the collaborations with other parties, that it starts bottom up. Because people want to start small, build something that works, and then when it works, then other people in the company get interested in it. And then an entire ecosystem will be born within a company. So usually it starts small. Sometimes some companies say we want to do a big bang, and then I usually say, please don't. Because that usually doesn't work. So it's good to take a use case, improve it, work together, and then go to the next.
I do think, though, that requires, once you're building such a small proof of concept, and you realize, oh, this may help other people, not necessarily will in the short term, but may. At that point, you know, take a step back from your proof of concepts, because that's research code, that's fine. But you have had your learnings. You now have done, or you have obtained the result that you wanted from your research code, and then you build it again. But now you build it in such a way that other people may be able to use it.
Any other question, Tony?
What are your suggestions for the academic researchers, especially PhD students? How far do you think is for them logical to go to make their research results production ready? Is that like a research, semi-research prototype code, or production ready, strictly tested, or somewhere in between?
I think that is this story here. Research code, in my opinion, should not be made to be production ready at the first get-go. Its purpose is different. If you build something, then that has a specific purpose, and you're optimizing for that purpose. In the research world, that is learning things, you know, solving your problem, actually getting to the results. And then we do have this stuff. Ooh, what happened? And then we have this story where we can collaborate on these open source projects. And then we can do multiple things. It depends a little bit on who it is, how well versed in, for instance, software building they are. They can provide their papers and talk with people integrating these things into the projects. And the people actually integrating it need some knowledge of how the papers work, right? If they can't read the papers, well, then it's very difficult to do this integration. But then if this collaboration happens on that level, and then a nicely built abstraction is made around it, then other people can use it, and then the papers will suddenly be used. So I don't believe that researchers have to build the open source project. They can, but they don't have to. But then the people who they foresee as the people building these building blocks, integrating these building blocks, integrating their work, please talk to them. Please make sure that this is made possible.
My follow-up question is that as a supervisor or industrial collaborator in this sector, when we make the research grant and research proposal, do you think it makes sense to actually include implementation to production-ready open source as part of the work package of the PhDs? And also, when acquiring, interviewing candidates, put that as one of the major consideration?
I don't think it makes sense to make it a hard requirement. I do think it's valuable to consider it. And then, especially if you're talking about research at the level of, well, not purely academic research, but applied research, that's already a different part of the research field. At that point, I think, like, if you have a learning, integrating it is, or not integrating it is not an option, I think. If you find something, it should be part of it. But then if you don't find something, what do you do? Do you still build this tool that doesn't do anything, that doesn't solve anything? So I think it depends on what you're researching. It depends on who you're talking about. Because not everyone can be a person that makes perfect code from start to finish and, you know, makes it available to everyone. That said, I do think that a paper without any application that still has a lot of good ideas that should be used, that can be used, and then not putting it out there, that's a waste. And then that's a shame. But I think that can be different people. That's my personal opinion. Then again, I'm not directly in the academic world, so anyone who is, please contribute if you want to. You probably have better ideas than I do regarding this. But that is what I foresee as the...
I think there's also a distinction between PhDs and PhDs. So you have PhDs that work fully at the university. And then we have PhDs, for instance, that work part-time at Alliander.
Yeah.
And I think there's a difference there because as a company, we also expect people to be more involved in production environments, etc. Where at the university, it might be 100% academic. So there can be a distinction there.
Definitely. Oh.
It will be unmuted from above.
Yeah. To add to Tony's question, we had a very similar, or actually exactly the same use case. We had two PhD students. One was trying to solve a problem of speeding things up to run things GPU native, and one was into power system research. So what we ended up is collaborating both of them to see how that solution actually also speeds up later. So that's also a solution, another way of thinking.
Definitely. And that's what you see on this picture, right? You have a research thing that contributes to a very small part. It can be a large part, but it can also be a very small thing in this bigger project. And that's also very useful at any level. And then collaborating on that is very good. Nice.
There's another question here in the middle.
Just follow on Tony's point with regard to open source and PhD projects. And also the fact that, yeah, some projects can kind of fail in the sense that maybe they don't give promising results, but it still makes that project valuable because what is not working and for the others to also learn from that aspect. I think an advantage of open source, or maybe just making it openly available, maybe that's a different concept, any PhD work or any other work, then also in connection with the article which is written, for instance, to that work, then it can be picked up by somebody else to improve that idea.
Exactly,
so
definitely.
I think that could be still a connection and then coming to the open source environment.
Exactly what you mentioned, right? There's a difference between open source production ready and open sourcing, making stuff available. I think, I know that There are people that disagree with me, but I am a very strong proposer of the fact that research should be open to everyone, in my opinion at least. And I think that this is a very large portion of that, actually. And also, it may lead to other research, completely unrelated, that actually will make use of that later on. So it's not a waste of resources. Even if you put it out there just like that in its researchy state, that's also a version that can be useful down the line. For sure.
Thank you.
There's room for another question if there is any. And if not, then let's give a warm applause to Martijn.
Thank you.
Thank you very much. Now, I have to skip through a couple of slides. There we are. All right. Then we get to the next use case presentation of today. The second use case presentation. It's called Peanut for Tactical Capacity Management, a Power Grid Model Implementation. So please give a warm welcome to Francisca Mestre.
Thank you. Yeah, hello everyone. Good afternoon. I hope you're all having a good day. My name is Francisca and I'm an energy data expert at Alliander. And for those of you who don't know, Alliander is a distribution system operator in the Netherlands. And at Alliander, I'm working with a team that builds midterm forecasts on the loading of grid assets for a process we call tactical capacity management. And we are doing that using Power Grid model. So today I will be covering three things. The first, what is actually tactical capacity management? Then the Power Grid model implementation that enables us to do it. And finally, two other use cases of this tool that I think are also worth showing today. So let's begin with some context and let's imagine ourselves as a distribution system operator. And for the past few decades, we've had two big responsibilities. The first is to make sure that energy reaches our customers at their homes and businesses at each moment of each day. And for this, we need our daily operations. So think real-time monitoring, emergency switching. At Alliander, this also means activating the redispatch market or calling off flexibility from customers. And this we call operational capacity management. Our second big responsibility is to make sure that the infrastructure remains suitable for the electricity needs of the future. So given certain electrification scenarios, we ask ourselves, where should I be making my system stronger in the next few decades, or which regions are in need of a new substation in the next few decades? And this we call strategic capacity management, and it typically involves building new infrastructure and projects that span longer periods of time. And then we have a gap in between. And as a DSO, we know that we will be facing congestion during this period. So the idea is that if we can know beforehand when and where we expect this congestion to occur, we can prepare ourselves better for it. And that's how tactical capacity management came to be. It is still a new process for us, a relatively new process for us. And it goes like this. The first step is, of course, to get insight into the bottleneck. We need to know when and where we expect capacity problems. And when we know that, we can, let me use this, yes. When we know that, we can analyze the measures that we have available to mitigate such problems. And at different locations, we may have different measures available. For example, in some places, we already have enough flexibility to help us mitigate the problem. But in other locations, we may need to look out for new customers who are willing to offer this flexibility. Another option could also be to request to reprioritize the investment plans from the strategic process. Or we could still consider temporarily shifting some load from a congested station to a station with more free capacity. So these are just a few examples of the measures we have available. And after analyzing them, we choose the measure or the set of measures that we think best fit a particular problem. And then when the time comes, we must carry out those measures, and then the process begins again. Today we will be focusing on the first step of this process, which is to get insight into the bottleneck. And that is where Peanut comes in. And I know what you're all asking, Peanut, what is that? And Peanut stands for Profile Evaluation as a Net Utility Tool. And I promise you that the acronym existed before we came up with the name. Yeah, and as the name hopefully indicates, Peanut is a profile-based grid calculation tool. And its objective is to give insight into the state of the grid given some demand profiles. I would also like to mention here that Peanut has a Dutch patent approved since, I believe, last year, and we are in the process of getting the European patent next year. So yeah, let's make this a little bit more concrete. And this is the process flow of Peanut. Like I said, we want to do some calculations on the grid. So of course, we need some topology information. And typically, our topology will look like this. We've got a energy source representing a coupling point to a higher level substation. We've also got our, where is it? Yeah, there it is. We've also got our primary substation with a high voltage rail, 2 high to medium voltage transformers, 2 medium voltage bus bars, a few medium voltage routes that bring power from the primary substation to the secondary substations, represented here by these shorter bars. And we have got some loads, and here these loads represent both medium to low voltage transformers, as well as larger customers with direct connections to the medium voltage rails. We are at this step using Power Grid Model IO to convert from our original topology files, which is Vision, to Power Grid Model. So we've got our topology, and then we go on to collect measurements and pseudo measurements from the past year and allocating them to our model. And at this step, we collect measurements from SCADA, which we typically allocate to the first sections of the medium voltage routes. We also collect some measurements from the prosumers, so either from the MVLV transformers or from the large customers, and we allocate them to the loads that represent these consumers or producers. And normally we lack measurements for the entire part of the grid we are analyzing, so to increase the observability of our system, we also make use of some pseudo measurements that colleagues of ours are calculating. And normally these pseudo measurements aggregate a load on the level of the secondary substation, which is what we see here. And up until recently, we were actually making use of the power sensors on nodes that PGM supported. That is going to be deprecated soon. So, together with the maintainers, we developed a solution, an alternative solution to enable us to still support these pseudo measurements. And then we send this model with topology and sensors to Power Grid model to calculate state estimation. And in reality, we are collecting measurements from the entire previous calendar year in 15-minute periods. So we are actually asking PGM to calculate 35,040 state estimation calculations. When that's done, we have got what we consider to be the most likely true state of the grid in the previous calendar year, which we say that's our base load. But we still want to look ahead. So on top of this base load, we also add information about expected future demand. And here we make a distinction between new connections that Alliander expects to be realized within the next 3 years, as well as autonomous growth, so the product of increased electrification of existing connections. And for these expected future demand, we create new loads in our model. And then it looks like this. We've again got our topology. We've got some green loads representing the base load, the output of the state estimation. Some red loads representing new connections. So for example, in the secondary substation, we expect two new customers. And some orange loads representing the expected autonomous growth at each secondary substation. And then again, we send this to Power Grid model and ask it to calculate 35,040 power flow calculations. At the end, we've got yearly profiles of the currents flowing through each cable and through each transformer in the part of the grid we are analyzing. And we compare that to asset limits to determine when and where we expect congestion to occur. And that is how we are using Power Grid model at the core of Peanut to support the tactical capacity management process. Peanut is implemented in Python, and it started being developed before Power Grid model DS existed. But I would also like to mention that we are right now in the process of incorporating PGM-DS into Peanut, so we can make use of its graph capabilities, and it just makes our we expect it will make our process in general more robust and handling model changes like adding new loads or adding new components more seamless. But Peanut is a pretty powerful tool due to its profile-based nature. So today I also wanted to show two other use cases for which we have used Peanut. One was a battery sizing calculation, and the other the calculation for a flexible contract or a capacity limiting contract. And let's begin with the battery. A few months ago, we received a request. There is a new customer who wants to be connected to our grid in 2030 with a capacity of 140 kVA on the consumption direction and 110 kVA on the feed-in direction. And we also know what type of customer this is, so we estimate its profile to look something like this. We see a lot of consumption during the winter months and a lot of feed-in during the summer months. And we begin our analysis by looking at what happens in the grid in 2030 before we even include this customer in our calculations, following the process I showed you earlier, where we establish a base load and then add already expected future demand. And what we see here is the profile, the yearly profile of the most loaded cable on the route where this customer wants to be connected in 2030. And we see in 2030, we already expect some congestion to be happening at this location. And then we analyze the impact of adding this customer, this request, into the route. And here we see all the time steps during the year where this customer will cause a negative impact on the grid, either by making existing capacity problems worse or creating new capacity problems, or by making existing voltage problems worse or creating new voltage problems. And these are the time steps during the year where we want to place a battery between the customer and the grid to prevent it causing this negative impact. So we must size this battery, and we need to answer two questions. The first, what should its rate of charge and discharge be? And the second, what should its capacity be? And to determine the rate of charge, we look at all the time steps of negative impact, and we take the highest absolute value of the customer profile to be our rate of charge or discharge, and that turned out to be 110 kilowatt. And to determine the capacity, what we do is we group all these 15-minute time steps of negative impact into larger time intervals, such that there is at least 12 hours between each interval to allow sufficient time to fully charge or discharge. And then for each of these intervals, we determine the energy content in the profile of the customer. And we take the interval with the highest energy content to limit our capacity, and that turned out to be 800 kilowatt hour. And finally, we also simulate what the expected charge and discharge profile of this battery would look like during the year. And we are, mostly we saw voltage problems. Here we are solving both for capacity and voltage problems, so we are seeing a lot of activity. And the last use case that I have for today was a calculation of a flexible contract or a capacity limiting contract. And for this case, we actually analyzed two requests together, and together they wanted about 4 MVA capacity on the consumption direction and 1.5 route where these requests want to get a connection is 4.25 MVA. Calculation of the capacity, so we do not assume behavioral profiles for these customers, but instead we just include them into our calculations as flat lines, so we can easily determine when the capacity causes problems, and we can know when we should be limiting it and by how much. And for these calculations, we analyze each direction separately. So here I'm showing first the feed-in direction, and we see in the target year we are still very far away from reaching the limit of the weakest cable. So we conclude that we don't expect any problems here. We don't have to worry about feed-in. We don't really need to limit it. For the consumption direction, the story is quite different. We do see, with all this requested capacity, we will be reaching the limit several times per year. What we do in this case is we share these periods of limit violation with our market services department, who need to combine this information with policy constraints on the type of window limitations we can offer a particular customer, to determine the most suitable capacity limiting contract for these requests. And in this example, we see that the longest interval above the limit lasts for almost 11 hours during a month, during the daytime in December. So an option here could be, to offer a contract that limits the consumption of this customer during the month of December during the daytime hours. And we can also calculate the total expected energy amount above the limit and the total duration of limit violation. And yeah, that is actually all I wanted to talk about today. Thank you for your attention. And if there are any questions, I'll try my best to answer them.
It's not a question. As a former developer of Peanuts, I just want to add that we have a pattern for this software.
Yeah, yeah.
And I believe it's been approved already, right?
Yeah, the Dutch one has been approved. The European one is still being evaluated.
So we're very proud of that.
Yes. Thank you.
Any questions? Two.
Maybe silly question, but I missed what pseudo measurements are really.
Yeah, so they're not really measurements that come out of sensors that are placed in the field, but they result of calculations which are based on actual measurements from other parts of the grid, or perhaps also assumptions, or aggregating a load from smart meter data which we cannot access individually due to privacy constraints. Yeah, I think there's other people in the audience who can tell a lot about that.
Okay, cool, thanks.
Hi, yes, thanks. Just a small question. You said you had you do about 30,000 state estimations for your calculations. How long, what time does that take to even calculate? Or what is the?
Yeah, it's actually quite fast. So the state estimation itself is quite fast. I think I haven't seen it take more than 3 minutes for some pretty large grids. Let me get back there. Okay, just this. Yeah, here. So in all this process, the part that takes us the most time is actually to download all the measurements that or pseudo measurements that we need, and processing them such that we can allocate them properly. But the actual calculations themselves just take a few minutes. For
thank you.
Yeah, for some pretty large grids.
I think the morning we just announced the removal of the injection sensor. I think your project is one of the main impacted projects. Can you elaborate how you migrate the situation to not to run into the problems?
Yes. Let me try to get there. Yes. So indeed, these yellow stars, they are here representing these pseudo measurements that aggregate load on the level of the secondary substation. And like I said, previously we were able to just place a power sensor there. That's no longer possible. So the solution that we came up with together with the PGM maintainers was to basically split the secondary substation in two nodes. We then allocate, we move these loads away from the original substation node to the new node that we create, and we then place that power sensor on the line that connects these two nodes. Yeah.
I would like to add, if you wish to migrate from the node injection power sensor, there's a full detailed guide on multiple ways on how you can do that. So you can check that out from our issue board.
Nice.
Thanks. Any other questions?
Thank you for the interesting presentation. I was wondering, how are you incorporating topological changes throughout the year into your calculations?
Yes, that is a very interesting question. So our topology, the topology files we are getting are only updated one time per year. And they only represent the normal grid configuration. Because we are mostly we have several use cases for Peanut, but at the moment we are focusing on tactical capacity management. So we don't really need to make, at the moment we are focusing on making forecasts assuming a normal configuration. We do face some problems during the state estimation process because our measurements will reflect grid configuration changes that our topology doesn't consider. But we are not actually incorporating these past topological changes into our model. We just assign higher sigmas to our power sensors during those periods to kind of let the state estimation give it more freedom to adjust to the normal configuration. We just don't have what's the word? Systematic way to access the information about past topological changes. Again, thank you. Oh, maybe just to add, I think if we could access this information, it would be very straightforward to incorporate it in PGM with the scenarios and connecting and enabling and disabling components. The challenge really is getting the information. Yeah.
I was wondering whether you could, because you mentioned you're only focusing on part one, like identifying the issue. And I was wondering whether you can give a sneak preview on what kind of measures you are analyzing. Is the temporary contract one measure? Is that, or is it something else?
Temporary? Do you mean the capacity limiting contract?
Yes.
Or, yes. So one of the measures is to rely on existing flexibility that we already have available, so we can inform with some time in advance our operational team that they should expect to activate such flexibility. Another option can be to look out for new customers who are willing to offer this flexibility, who are willing to accept capacity limiting contracts to help us. I also heard in the morning, or actually Martijn, mentioning about making most use of the assets. So at Alliander, there's also a sweating the assets initiative, so we can really push the usage. Yeah. Reprioritizing investment plans that are already planned, but maybe we can shift them a bit to solve the most pressing problems first. Yeah, but definitely capacity limiting contracts and flexibility are a big part of it.
Thank you.
Another question? Yeah.
How do you deal with uncertainty? Because your historical measurements are just one snapshot of what happened, but many other things could have happened.
Yes. Yeah. So our forecasts are still a deterministic forecast, basically. We are assuming that the information we have is correct. And then during the process of risk assessment and analyzing the measurements, we as humans are considering that there is some uncertainty, but they give us some indication. We are exploring with other teams in the company who are building foundation models, grid foundation models, and machine learning techniques to predict with some bandwidths expected future demand. So we are starting to explore with them how we can incorporate that in our process. Yeah, also exploring with other teams in the company how we can consider steering actions on the customer. So flexibility call-off that happened in the past, how we can make sure not to carry those over to the future. So yeah, there's a that is a point of work.
All right, there's time for one final question, if there is any.
Hello. In your presentation, you are focusing on the technical capacity management. The period is from 2 years ahead to 3 years. And in your last case study, it shows that there's a forecast for like after 10 years. So what's the link between that use case to the technical capacity management? Could you please elaborate it a little bit?
Sure. Sure. So the process of Peanut actually works for the process of Peanut works for any time span. Just the input data that we give it determines it determines our scope. So the last 2 use cases I showed, we worked on them last year, and last year we were mostly getting requests like of this sort. Can you please help us analyze what's the impact of this particular request or this particular customer? And then we could work with whatever target year was requested. The 3-year time span is really the time scope of tactical capacity management. So when we are using Peanut for tactical capacity management, we are only considering, considering the expected connections that will happen in the next 3 years and the expected natural growth that also will happen in the next 3 years. But then it's all about the inputs.
Thanks.
All right. Thank you very much, Francisca.
Yeah.
Let's give her a warm applause. Yeah, you can leave video. And now it's time for a break. So please stay within the auditorium. You can use the bathrooms in the back. Cake will be served at any moment because, as Santiago mentioned this morning, we reached more than 10 million downloads with Power Grid Model worldwide. So that's something to celebrate. So there will be cake. For the people online, we'll be back, or we hope to be back at 2:40 p.m. We have to slice a cake here in the room, so let's see if we can manage in 15 minutes, and if the cake is delivered in time. So hope to see you soon, and let's enjoy the break. All right, we're going to start again. I hope you all enjoyed 10 million downloads cake. I did, and we only got 5 minutes past time. So past schedule, so that's pretty nice. Now it's time for our next use case presentation, which is by Udo Schmitz and Eduard. They have done multiple contributions to the Power Grid Model project over the last couple of years, and they will talk about their latest contribution. That's PV nodes in PGM power flow. So let's give them a warm welcome, and then I'm also giving them their microphones.
The first problem. Okay.
All right, there you go.
Good afternoon, everyone. I hope you can hear me. First time I have a headset. Today we talk about PV nodes in Power Grid Model and PV node is not photovoltaic. It's power and voltage. So, okay, first slide. A few words to us. I'm Udo Schmitz. I'm a chief engineer and grid analyst at SOPTIM AG in Germany. And I'm contributor to LF Energy Power Grid Model. And this is my colleague Eduard. He's senior software developer and data grid specialist, also working at SOPTIM. And he's also a contributor to LF Energy Power Grid Model. And so today we have two parts. I will give you some smart theoretical backgrounds, and my colleague is talking about the practical issues to aspects of implementing PV nodes in Power Grid Model. So what's the motivation? Here are some questions. There are two of them, why we add PV nodes to Power Grid Model and why they are important. So the answer is very simple. Power Grid Model didn't support PV nodes. And you need them not in distribution grids. There are PQ nodes already fine, but in transmission grids, you need PV nodes because there are many generators who control the voltage. And for the upcoming support for distributed slacks, you need also PV node support. And we implemented it. But now some theory. What are PV nodes? Normally, you know PQ nodes. The given values are the active power P and the reactive power Q. And the solver solves for you the complex voltage magnitude, and voltage angles. PV node is quite different. It's for if you control the voltage stays at the level you set it, and then you have two values given. It's the active power P and the voltage V magnitude. And the solver has to calculate the voltage angle and the reactive power you need to stay on this voltage. So what's the typical equipment behind PV nodes? In classical, there are synchronous machines. In conventional power plants, there are big machines behind a transformer. And nowadays, we have also inverter-based resources like wind turbines or photovoltaic inverters or battery storage. They can also act like a PV node. But a PV node is only a model. It's only a model for the physics. It's not a real thing, and it's only it works only along as the device can operate in its operating limits. So a little joke: Bakoni power plant is not a PV node. So it's not photovoltaic, it's power and voltage. And now we enter the theory part. Don't be afraid, don't worry, I keep it short. Here's the question: how does the Newton-Raphson system behave when we turn a PQ node into a PV node? And this is the first equation system. It's the classical Newton-Raphson Jacobian formulation. You see, here's the mismatch vectors. Where are the Q and P deltas? And this is the solution vectors. This is the what we want to find in the system. And this is the Jacobian, which contains the derivatives. And there's also a compact formulation, you know. There we have the H and G and L block. H and L are the derivatives for the active power, and G and L are the derivatives for the reactive power. So you can rearrange those equations, so you can relate these equations to bus pairs. And when we do that, see it on the next slide. We have the system becomes quite easy, I think. Above, we have a 5-bus system, consists only of PQ nodes, and the slack is removed from these equations. So we have the bus 2, 3, 4, and 5. And these are so-called supercells. Therefore, we rearranged these equations. And if there is no electrical connection between neighbors, between bus 3 and bus 2 is no connection. Therefore, bus 3 and 2, where is it? Sorry. Maybe it's wrong. Yeah, this is 0. Bus 3 and 2, you have no connection. Therefore, you have the 0 supercells. So what to do if we change the PQ node at bus 3 into a PV node? What changes to the systems by keeping the structure of the system? Then this L relates to the reactive power, becomes a voltage, and on the other hand, or 0. So this is this thing we did. We keep the structure of the Jacobian and replace those equations. Inject other values in those equations. And the same thing happened to the mismatch vector. We change. Oh, it's not working. We change the reactive power equation of bus 3 with a voltage value at the bus 3. So we keep the structure and the vector position, and this has a big advantage. The next slide. Yeah. So the matrix size remains unchanged, and the PV to PQ switching becomes much easier. Normally, you could also erase some columns or rows from the equation system, but then you change the structure of the Jacobian. It's not so good to handle. So far, we have discussed why it's not working. Implementation. Oh, sorry, I've forgotten on some slide. The implementation. There are two different approaches. In classical systems, we mark the bus as a PV bus. You say only this is a PV bus or this is a PQ bus. But in Power Grid model, we introduce some voltage controllers, and we then can see what is on the bus connected, and then could say, okay, it's a PV bus. You don't mark it as a PV bus. I think no, this is the wrong direction. Sorry for that. What is the problem here? Okay. Okay, so far we are ready or done with the PV nodes formulation, and I will give you a short outlook. There are two things we want. One thing we want to do, and one thing there we are already an issue. The next thing we want to do is to introduce the PV to PQ switch. If we come to a limit with our reactive power, you cannot hold the voltage at this given set point. So you have to do something with this situation. And one approach is to change the PV node into a PQ node, or you can also change the tap of a transformer. If the generator behind a transformer, you can change the tap. So we have the more reactive power. Yes. But it's not implemented yet. It comes in the next few weeks, I think. And the next thing is more related to distribution grids. They are so-called voltage-dependent control systems. You have a function. Q is a function of the voltage. So you cannot say that this is a PV node. It's a voltage-dependent node. And we call it a soft PV node. and therefore is already an issue given, and I give some aspects to this issue. So I hand over to Eduard.
Hello, my name is Eduard, and I will be talking about the practical usage of voltage regulation. As Udo has mentioned before, the Newton-Raphson algorithm works with PQ and PV nodes, but the data model does not specify the node type directly, and previously a node type was not needed, as all nodes were implicitly PQ nodes. So now we still don't specify a node type, but instead have created a new component, the voltage regulator, with attributes for a regulated object, which can be a generator or a load, a status to turn the regulator on and off, a reference voltage to which the node should be regulated to, and also reactive power limits. They're optional and they're currently not used. I will come to that in a bit later. So a PV node then is a node with at least one enabled generator or load. Which is then referenced by an enabled voltage regulator. So it is derived at runtime. This is how you would define a voltage regulator in code. It's straightforward, works just like any other component. So there isn't really much to show here. So let's instead look at some examples. So we define a small network with 3 nodes in the 110 kilovolt voltage level. There, node 1 is a load with 250 megawatt and 100 megawatt. Node 2 is a generator with 200 megawatt and 80 megawatt, and also a voltage regulator connected to it. And then node 3 is a source that should provide the difference between the two nodes. And for lines, we have a short line with low impedance between the load and generator nodes, and long lines with high impedance between the source and the other nodes. And therefore, we would expect a large voltage drop at nodes 1 and 2 in this example. So in the first example, we start with no voltage regulation. We set the source reference voltage to 1.0 per unit. And we see the calculation or the power flow results in this table. The table combines node data like voltage or bus injection values on the left side, and on the right side the power flows or the outgoing power flows of the branches connected to the nodes. And as expected, we see the voltages at nodes 1 and 2 are quite low, so there was a significant voltage drop. And we also see that without voltage regulation, the generator at node 2 provides the specified reactive power value of 80 megawatt. And if we, as an additional information, if we calculate the network losses as the sum of the power flows over all branches, we get quite large losses of 26 megawatt and 60 megawatt. So we change the network a bit. So we increase the source voltage to 1.1 per unit, which is 121 kilovolt. And then we see that nodes 1 and 2, they're getting closer to 110 kilovolt, but still node 1 shows a significant drop. But with this configuration, the network losses are a bit smaller, 15 megawatt and 30 megawatt. So finally, we enable voltage regulation and see what happens. So first we set the source voltage down to 1.06 per unit. We enable the voltage regulator at node 2, set its reference voltage at 1.08 per unit. And now we see that node 1 reaches the desired voltage of 110 kilovolt. And you also see that now the generator at node 2 provides a calculated value of 137 megawatt instead of the specified reactive power of 80 megawatt. Yes, and again, the network losses are a bit smaller. Now it's only 12 megawatt and 22 megawatt. So this is how voltage regulation works in this small example. So let's look at some possibilities and limitations of the current implementation. So we support symmetric and asymmetric power flow calculations with the Newton-Raphson method. Other calculation methods like linear or iterative linear are not supported. Then currently we support one type of regulators in the network. So you can use a voltage regulator or a transformer tap regulator, but not both at the same time. As regulated objects, we support appliances like loads and generators. Other appliances like sources or shunts are not supported. Well, sources, for example, because they already regulate voltage. So if we connect a source and a voltage regulator at the same node, then only one of them can be active at the same time. However, we support connecting multiple voltage regulators to the same node, provided they specify the same reference voltage. And in that case, what happens is that the remaining reactive power of a node is then distributed equally among its regulated appliances. And the remaining power is just the calculated bus injection minus the specified power of the unregulated appliances. So we see this distribution in this table. For a different example network, the table is a bit different from the previous tables in that it shows connected appliances on the right side. And so we see for node 30 that it has 2 regulated appliances and 1 unregulated appliance. So if we take its bus injection value of 137 megawatt, subtract the minus 30 megawatt from the unregulated appliance, we get 167 divided by 2 for the 2 regulated appliances, and we get the 83.8 megawatt as highlighted in yellow in the table. And the same procedure is applied to node 40, where we have 2 regulated appliances. I've mentioned reactive power limits before. They're currently not used, but when they will be used in a future version, then this distribution may not be equal anymore, especially in the cases where the distributed value would violate the limits of a particular appliance. And that's it from us.
Thank you.
Thank you for your attention.
Hi, thanks for the presentation. I understand what to think of a PV node in transmission systems. It's the bigger power plants, right? What should I think of in distribution grids?
For distribution grids, I mentioned these inverter-based resources. Maybe therefore it's important, but we use it for transmission grid, to calculate power flow in transmission grids. And we also worked on a CGMES to PGM converter, and we missed this feature. And so we can't use the power flow from power grid model. We only use the state estimation part. And therefore I talked to Peter, why don't we introduce PV nodes? And the answer was, yeah, we don't need them in distribution grids. But now they have this ticket issue with the distributed slacks, and therefore you need this PV node to solve this problem.
Can I ask one more question?
Yeah, go ahead.
In the last example, you showed that you distributed reactive power over nodes. But maybe I'm missing something, right? There was a...
Yes, it's so if you see on the left side, the node is repeated. The node ID is 3 times 30 for the 3 connected appliances. So I distribute the the power injection value of the node to the connected appliances, because only the appliances can take the power.
Gotcha. Okay.
There's nothing else, only appliances.
Thanks.
Any other questions? Yeah.
Yeah, thanks. So also for my understanding, because I didn't know PV nodes. So you said that one way of that in reality the transformer might regulate the voltage, but then you could also have modeled this transformer explicitly in the model and set the voltage regulation on the transformer, right? On the tap changer behavior, or wasn't that a possibility?
You need a generator to have a voltage regulation, but if you at the border of limits, you can switch the type. That's one resolution, but it's better to change a tap. If you change your tap, it has an effect on the reactive power.
So there's a difference by changing the tap. It goes incrementally, and in this case, in a PV node, you fix the voltage, or at least you try to fix the voltage of that node. Any other question?
Just in addition to the discussion which technologies in the distribution networks, I have read once that heat pumps, they could behave as a PV node. So there were some empirical tests on how they impact the voltage. But at the same time, I have not seen any study in the Dutch networks on this. So that's a candidate that we should look into, I would say. And because we have more and more heat pumps entering into the networks. Other than that, I was a bit curious about the not being able to limit the reactive power. So, for instance, when you are modeling solar PV in the network, then it has the apparent power limits, capability P square plus Q square, less than apparent power, etc. So how do you model then these aspects in the power flow calculation?
This is the first step. So now the limits are infinitive. There is no limit. So you make the calculation, and the calculation says, okay, there are 100 MVARs reactive power, maybe, and it's just to look, oh, the limit is raised. But in the next step, we take the limits into account and do something if the limits are raised. So for the heat plants?
Heat pumps.
Heat pumps, I think they have a very, very small reactive power limit. So I would not suggest to say that it's a PV node. And if it's behind the meter, then it's not a PV node. It's the same thing as a balcony power station. That's not a PV node. It's behind the meter. Everything behind the meter is just a PQ. Don't use that as PV node. And the Q limits are too small. They're near 0, I think. So the solver would switch that.
No, the Q-related thing was a separate question that I had.
If you accumulate many of heat pumps, yeah, maybe it's a good idea to say this is a PV node.
Okay.
In that case, but not for one customer.
No, not individually. Thank you.
All right. Another question?
Why is the derivation only available for the Newton-Raphson? Can it also be done for the other solver with the solver of PGM?
In the state estimation, you don't need PV nodes. There's no demand for that. The equations are other. And in the DC solvers, I don't care, I don't know.
So we have another iterative power flow solver, and theoretically we can indeed add a PV node over there. However, yeah, I guess it's what we need to do is very defined here, and then yeah, it won't add any special value if we implement it over there as well. That's one way we thought of it.
So usually we implement things first in Newton-Raphson because that's the method most people use. And then if there's a use case for it, we can implement it in other methods as well. So maybe in the future, and maybe you even want to do it. Last question.
Welcome.
The first sentence of PGM website is, or the homepage is that power grid model is a distribution steady state calculation library. Do you think after this we still can keep like that, or do we need to change that framing?
The power grid model is your distribution system, but with our change, we can also use it for transmission grids in some cases, I think. There's no difference. Newton-Raphson is Newton-Raphson. There's no difference.
This definitely increased the use cases that we can do with power grid model. Thanks. Give them an applause. All right. So now we're already at the final part that we're doing in this room, and that's a lightning talk. So in the coming 20 minutes, you'll hear 4 very interesting stories, really short, and probably a lot of food for thought and interesting talks afterwards during drinks. So I would like to welcome the first person forward to talk about the digital twin LS flex model, and that's Willemijn Brus.
Yeah, okay. Hi all, I'm Willemijn. I work at the DEP, which is a department in Alliander. Works on project-based consultancy department, and I work in the data science team. And I'm here to tell something about the digital twin LS flex model. The model gives quantitative insights in the impact of flex measures on the low voltage grid. And it also takes into account what the impact is on the cost and the comfort of households and on the CO2. Yeah, so the model was developed to give some more insights in questions that arise when you think about using flex on the low voltage grid. So what is the most affordable system? What will happen with the prices if you do some price optimization? What does flex mean for the comfort in households? So if the grid operator wants to use flex to mitigate problems on the grid, what will it mean for the households? How often will the grid operator intervene? So questions like that kind of questions will be answered with the insights of this model. Yeah, and the first studies show that actually we can get a lot more out of our grids if we use them better. So if we use flex to make better use of our grids. And you see here on the image or in the visualization that the model moves the load from like moments where there's a lot of load on the grid to moments where there's less load, or if you have price optimization, to moments where the price is cheaper. And for the PV, it will curtail when there's like congestion and in an honest way. Yeah, so this is a little bit about the model design. So it is a load flow optimization also, so it uses power grid model and optimization for depending the objective, so price optimization or mitigating grid congestion, and therefore it uses some kind of assumptions on how many cars, how many heat pumps, how many solar panels, how many batteries, of course, the topology of the low voltage network, some kind of climate year assumption, and adoption of how many households will join the steering. So like adoption HEMS. And some characteristics of the buildings and isolations to get a good load estimation of the heat pump load. So first what we do is actually for every connection in the grid, we try to get a load that's composed of the base load, composed of a car if they have a car, composed of the heat pump profile if they have a heat pump, and also a battery if they have a battery. And there is some randomness in that because if you have adoption, for example, of 60%, it's random which household gets like the car or the household or the heat pump. So you do it several times to get some insecurity range. So you do that with Monte Carlo. And then we do a load flow with Power Grid model, and we see what the situation on the grid is. And then actually the actual model of digital twin takes into part. And that's the steering. So that's like either the steering for mitigating congestion or steering to optimize for the prices of the households, or a combination where you do first the price steering and then mitigating the grid congestion if new peaks arise from the price optimization. And then in the end, we show what the insights or the results are on the grid, on the comfort of the household. So what's the inside temperature? Still okay? How many impact did it have on the sessions of loading your electrical car? So stuff like that. So we say it's honest critical peak steering, and what we mean is we take into account which household was steered, and then if you steered in the time step now, the chances are the lowest that you will steer in the time step afterwards. So that's with the critical steering, and that's how we take into account to make it as honest as possible. And we steer on the transformer capacity and of the feeders of the grid. And for the voltage, we steer on the nodes. So what's really nice about this project is that we started with an Alliander. So we started with corporate strategy, asking us to make a model to give some insights in the question I showed before. But now actually we are continuing our development with Netbeheer Nederland, Emsys and Stedin. And that's really nice to actually get more uniform and transparent insights in the impact. We recently did a first study together, and we were actually discovering that we had a lot of discussion about the underlying assumptions. And we're going to take the next months to get more consensus about those underlying assumptions. So that actually, I think, shows how important it is that there are collaborations like this, because the model gives all kinds of results already. But before we can all stand together behind the results, we need to agree first on all the underlying assumptions. And right now, that's not the case yet. So the coming months will actually be more focusing about what do we think about the price optimization, how sensitive should it be? Should it really be like 1 hour that all the load gets because it's the cheapest, or should it be spread around some hours? So underlying assumptions like that are very influencing the conclusions. We're going to take the time to get more agreeing on those assumptions. So we do have ambition to make the model and a dataset also open source. And we started with making it sector source, which means the code is now available for the developers in Stedin, Emsys and Alliander. So that's the first step. But before we are going to make it open source, obviously we all need to stand behind the actual model and the assumptions, and we are not there yet. So I would say that the open source ambition is a little bit farther away than the first coming steps. So that's, I think, what I want to tell you. I don't think we have a lot of time for questions, so you can approach me later if you want, but thanks for the attention.
Thank you, Willemijn. And then we go straight to the next, which is about Power Grid model meets DOTS co-simulations. So please give a warm welcome to Leo van Schooten.
Yeah, so thank you. I'm here to tell you something about our solution for bridging the gap between academia research and actual usable software models. So first things first, I am a scientific software engineer at the TU Eindhoven, and we've developed the DOTS co-simulation platform in cooperation with TNO. It's a platform that in which the aim is to take away the software engineering complexity for researchers when they want to investigate something using co-simulations. Of course, the complexity still remains in designing your co-simulation. So which simulators or models do you want to use? What are the timing requirements, etc., etc. And we have utilized this platform already in, for example, the GoE project. Maybe some of you heard of that. And we are now also incorporating it in current projects, amongst which is the EASY project. So what is co-simulation in short, for maybe the people who are not familiar with the concept? The main idea is that you have a lot of different models of an integrated system. So you might have like a battery model, a wind turbine model, household model, weather model, whatever. These all can form one coherent system. So the energy system is, of course, a very suitable candidate for this. And the idea is that these models all have their own very specific implementation, which can do very specific things or not, and that you can easily plug and play different kind of models. So, for example, let's say we have a household model that optimizes for a certain energy contract or control paradigm, and we want to test what the impact is on the network. We might have one household model that optimizes using a dynamic contract and one that only has a static contract. And the idea is then that you can simulate them together or just plug and play with the household model and see what the differences are, while the rest maybe stays the same. Yeah, so what is the design philosophy of the co-simulation platform that we have there? Is that it should be modular, so researchers should, in theory, be very easy, integrate their own models in it, and also reuse other models that other researchers might have used or developed in the past. It should be scalable, so yeah, whenever you want to run bigger simulations, the step from local testing to, I don't know, maybe a big cluster should be quite easy to make. Scenario should be as you should be able to define your simulation scenario as easy as possible. So that's why we opted for a scenario file, which describes your whole layout of your energy system, so your grid, your loads or households or generators or weather or whatever you need. You can all include it in that file. And of course, we would like to provide tools to actually read the output as well and visualize it in a nice dashboard. So those are the 4 principles that we designed DOTS upon. Yeah, so from a user perspective, if you would want to use the platform, you would first define your scenario. Then you might look into the models that are available and select the ones that you need. Then you execute it, then you analyze, and maybe you come to the conclusion, oh, this was wrong or whatever, and you start again, or you have some nice data and draw some conclusions out of it. Yeah, so how does Power Grid model fit into this? As I showed you in the first picture, there was also this network simulator. So of course, in a lot of energy system studies, we also want to know something about the electricity grid underneath it. So that's why we wanted to use PGM. And the version that we have now uses OpenDSS, but we want to transition to Power Grid model. And that is mainly because with the outlook to the future, Power Grid model is probably going to be a bit better supported. Support is also never far away because, yeah, we have Tony in our group, for example. And I have made my contribution to Power Grid model as well, so I also know a thing or two about it. And we had a bachelor student that made the first step into transitioning to Power Grid model, but yeah, we want to, of course, make the full transition to it. Yeah, so that's it. Here are some nice GitHub references, and I think that was it.
Thank you, Leo. And we go straight to the next, which is about KOPR, an AI digital twin deployed nationwide in Luxembourg for smart grid operations. So please welcome Cyril Cecchinel.
Thank you very much. Hello, everybody. So my name is Cyril Cecchinel. I am a project manager at Architect at DataThings. I'm going to present you KOPR, that is actually our digital twin solution that is used today by Creos, the main DSOs in Luxembourg, for their daily operations. Just a few words about DataThings. We are located in Luxembourg, and more Luxembourg City. We have been founded in 2017 as a spin-off of the University of Luxembourg. Our motto is to help companies moving from reactive operation to live predictive-based decision-making. And to do so, we have a technology that is called GreyCat, that you can see as a graph and temporal databases, that is at the core of our projects. Almost 10 years ago, we have been approached by Creos that was facing the challenge of energy transition. We already spoke a lot about it, but just for 10 seconds, you know that at the low level voltage, we have more PVs, more EVs, more heat pumps, and basically we have a lot of things that was not here before that is not transforming these networks. And Creos basically wanted to have a better understanding of its grid based on this new motto about the energy transition. At DataThings, to do so, we have developed a solution called KOPR that is modeling this grid. In the context of Luxembourg, on the grid, we have more than 1 million assets, 350,000 smart meters, almost the same amount of cable, and basically per day we are collecting more than 100 million measures per day, because every smart meter produces 4 different kinds of values every 15 minutes. So our task basically was to assess the cable load to know that if the grid was behaving well, that we have no congestion, nothing going wrong on the grid. Before KOPR, to do so, it took Creos almost 8 hours to compute the state of the grid. They came to us and basically they wanted to improve this score of 8 hours. And especially they had as well other questions, how to get the finest grid status data, how to increase the accuracy of their load predictions, how to reevaluate the simulation of the grid every 5 minutes, how to simulate the impact of EVs, PVs, heat pumps, connection requests. And because of data privacy issues, they wanted to have everything on premises. So we end up with KOPR, that is our digital twin for smart electricity grid, powered by our GreyCat technology. You can see it as a digital twin, merging different feeds from different kind of sources. We have data coming from the ERP, we have data coming from GIS system, we have as well weather forecast services to know the forecast for the next days. We have individualized AI models, basically to compute prediction on the loads. We are collecting a load profile from all the smart meters, and we are training in real time models and more different kind of models to compute prediction for these load profiles. With so, they are scalable and efficient. They can analyze and decide in seconds, and it has been running no more than 2 years in production in Luxembourg. So the project, actually we have data for 4 years, but now it's really in production for 2 years. And we are trying to get outside Luxembourg. We have some pilots in Switzerland, and as well we have offers sent to Austria, Poland, Germany, and in the GCC countries. And here I have video, so very quick about KOPR, where basically you can see the countries and you can see every single substation modeled in KOPR. And if you zoom in, you will see all the connection points, the cable, and ultimately the meters with the load curve for every inhabitant or companies in Luxembourg. In terms of power flow computation, as I said before, it was taking 8 hours. Now for a single grid configuration, it took a bit more than 3 seconds to compute one state of the grid. And I'm here today because recently we switched our power flow model to use the PGM one. So thanks. As I said, AI is at the core of our product. We are not looking only at the load profile, but as well, it's very important to us to know the date, the time, and the weather condition, the holidays period, and not only the Luxembourgish one, but as well as the French, the German, and Belgian one, because we have a lot of cross-border coming to Luxembourg. We are doing profiling per customers, and we have several models that are competing to each other. We have LSTM, we have Gaussian mixture models, we have exponential smoothing models. And these models allow us to compute the load in the cable. To look at the future, we exploit these models as well to extrapolate the load in the cable for the futures. AI is not the only, let's say, added value of our product. We have as well, a strong component that is simulation, where basically we can simulate everything. In KOPR, let's say, you can transform your grid as a Lego. You can play on every asset of the grid. You can go to a cabinet. You can open, close some fuses, and see how basically the load will be reflected on the grid. We can as well add simulated load profiles to houses, to companies, if you want to simulate photovoltaic installation, in pump installation, or EVs. And they are using this solution basically to do the connection approval today in Luxembourg. We have as well some policy simulators. Let's say you are in a city or you're in a district, you can on the map draw a rectangle and say, in this particular region, I want to simulate the installation of 40% of photovoltaics, and you can after see the state on the grid, if it's going well, if it's going wrong, if you have to change a cable, if you have to add new cables. Well, everything can be simulated on the grid. Just a last remark. Why, as a company, we are here today. It's our first participation to the PGM Meetup, and I hope it's the first of many others. We really want to be a part of the community because, as I said, we have migrated our power flow engine that before was our own implementation to the PGM one. First, it's an open source one. We see that there is a lot of traction on it, and when we discuss with clients, it's always nice to say that we are using an open source implementation. It's always put confidence, meaning that it's used by other people. It's just something, not just something us as IT provider has developed. So that's why we switched to the Power Grid model. KOPR is today used in Luxembourg every day, and as I said, we are targeting smaller DSOs abroad, especially in Switzerland. So we will get feedback on our deployment of KOPR and about the powerful computation. So that's something that we are really keen to exchange with the community. We want to share some lessons learned, and as well we see strong collaboration with TSOs and DSOs. And the last point that is not on the slide, but I would like to share is our GridCAD technology at the moment is closed source, but we want to open its core concept to the open source community. So as well, we are looking some advice, some support for people that have already been through the process of maybe dealing with the Linux Foundation or the Eclipse Foundation to get a bit of a guidance or advice. That's why you are here. Thank you for your attention.
Thank you, Cyril. And we go to the last one, which is about how to best lift transmission constraints. So please give a welcome to Wadman.
Thank you. So last talk, I'll promise to keep it light. How to best lift transmission constraints. I'm Wander. I have a background in modeling and simulation of power grids, and also at Alliander, I do exactly the same thing. First, I'm not going to discuss Alliander because by now I think you should know what Alliander is after today's talks. On the right plot, red means bad, so we also know that. So let's continue. So I'm working at Team IMPI, Integral Net Planning with AI, but forget about the AI. There won't be any AI in these slides. So the goal of my team is to quantify long-term value of investments in our grid by simulating the grid and by simulating the impact of various investment strategies on our grid. And the scope is really Alliander's entire medium voltage grid plus some HV points for 5 to 40 years ahead, so long term, way longer than the peanut scope. And well, we do this simulation using PGM and PGM-DS. We start with the current grid of this year, and the grid model consists of nodes and branches, and the nodes denote some HV-MV transformers, but mostly secondary substations, like 30K of them, as you can see in the red plot. Low voltage networks are not modeled or abstracted away behind LV rails. Branches are either transformers or lines, and within each 2 points there's just one line modeled, so that it's comprising of all cables and sleeves that are actually between those 2 points. And I'm gonna give you some hint of what's in this simulation. So there's more, but just to give you some sense of what we actually model and simulate. Suppose here this small grid, which is one substation. We have a budget in euros and human hours, electricians that can do stuff. And what can happen in our model is that there's some excavation damage. A line breaks down or a line overheats. That will actually need to be replaced, which will cost some money and some human hours. And will also incur some people being in the dark. So the SID is kind of the average amount of time that an average customer will be out of power. So that's a KPI of the simulation. So that will happen. Also, new clients will be wanting to get connected, and existing clients will want to be expanded. So here you see 3 of those, and we will actually try to connect them by designing connections and expansion. That's happening in the simulation. After that design is done, we have to actually compute whether that's a feasible situation. We use the power flow. That's where PGM also comes in. And we, for example, see that there's a capacity issue in a line or a voltage issue in a node. So we actually monitor those on the bottom right. What's the, over there. We try to lift transmission constraints, because then the clients get connected and then we're more happy, by either upgrading cables, finding new routes, and by doing so actually find ways to actually lift constraints. So the transmission constraint is actually the number of transmission constraints going down. Of course, this also costs money and human hours. That's what it is. And by doing so, we can simulate the future in one way. We can repeat that by actually do it again, but then implementing a certain strategy. For example, having more flex contractors or whichever strategy that also has been discussed by Francisca and by Martijn, for example. And we can then compare those 2 simulations and actually compare the KPIs of those simulations. For example, the number of transmission constraints that were still in there. And by doing so, we have some quantification of the impact of our strategies, which is all good. But if there's one takeaway for you guys to have from this slide is kind of some appreciation of the complexity behind finding out how to lift a constraint. Because maybe in this small example, it's relatively simple what you can try out to lift the constraint, but consider you have thousands of nodes and hundreds of clients that want to be connected. It's, at least for me, not clear what is the best investment you could do to actually get the top 20 clients from the waiting list to get connected. So I was hoping people of you have already some experience, best practices, and can approach me after this talk to discuss what to do here. And maybe there's even some solution that we can implement in PGM. I don't know, but let's see what comes out. Thank you for your attention, and have a great rest of your day.
Thank you, Wander. All right. Then we're already at the end of the day, at least the end of the day in this room. So I'll have some closing slides, and then afterwards we'll go on a tour through the data center that will lead us to the drinks afterwards. So first of all, our goal is a community-driven ecosystem where we all work together, collaborate, and bring the project even further. So you can think big, think working groups, hackathons, brainstorms, tutorials and workshops, consultancy, webinars, anything you can come up with. So if you have any ideas, feel free to pick it up yourself or just contact us, and let's see what we can do together. As a reminder for you, you've heard it a couple of times throughout the day. If you have any new ideas for features or improvements, please create an issue for any ideas you have on all of the issue boards for the separate projects, or talk with one of the maintainers during drinks if you're around here physically. So if you want to stay updated on the project, there are a couple of things you can do. First of all, you can join our community meeting, as mentioned already a couple of times throughout the day. We have a community meeting once every 8 weeks. We, as maintainers, will give some updates on what we've been working on and what we will work on in the coming 8 weeks. But there are also small presentations from people in the community. There's room to ask questions, bring up any ideas. If you have a new feature request that you want to discuss with us, come to the community meeting and you can discuss it live with us and dive into more details. You can also subscribe to our mailing list, so then you get announcements if there are any to make, so you'll know when the next meetup will take place, for instance. But also if we have new releases or if there's anything else interesting to mention to you. If you're interested in our roadmap, you can also see that online on GitHub. As mentioned throughout the day, it's open for change. So there's a roadmap now, but 1 year from now, we will probably have done different things than you see currently on our roadmap. But at least you stay up to date on things that we're actually working on right now and what is on our planning. And that also gives you some, well, you can give us some input on the roadmap as well if you have other ideas that need to be on there. And if you have any questions or want to discuss some things with us, you can also use the discussion board to discuss your things with the community. Usually the maintainers will reply as well, but others from the community sometimes reply and answer your question as well. So to close off, it was already mentioned this morning, if you want to contribute to the project, first of all, if you use the library, you can give feedback, report bugs. That's already really valuable to us. A second layer you could be working on is providing validation test cases. You could improve the Python API. Again, if you really want to dive into the core, work on the C++ core with new algorithms or new models. And there's a list of good first issues. So if you want to get started, there are some issues that we picked for you that are quite easy to work on. So that's a good starter to get familiar with the project. Then we're really at the end of what we're going to do here. So I had an amazing day. I hope you had as well. I got really inspired by all the presentations. So many interesting things going on. I think there's too many topics to be discussed in the drinks afterwards. Also really looking forward to that. And looking back, I think it's really nice to see all of you here, also online. So many different companies that subscribed. It's really nice to see the community growing. The cake was well, for 10 million downloads. That says something. But it's also nice to actually see various companies working on the project and talking about what they've been doing. So to close off, special thanks to Brightcubes and Interconnect for hosting the day together with us. I'm looking back at a really great Power Grid model meetup, and that's also thanks to all of you. So, and also special thanks to the speakers, of course, that inspired us all throughout the day. So thank you all.